Welcome to the Nutanix NCP-MCI version 6.5 certification course, where we will methodically deconstruct the architecture and operational demands of the Nutanix platform. This introductory module is designed to align your understanding with the official certification objectives while laying the groundwork for mastering the software-defined data center. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to Nutanix in any way. All trademarks belong to their respective owners. In this course, we will explore the core tenets of hyperconverged infrastructure by dissecting the Nutanix Enterprise Cloud Architecture and the AOS stack. You will gain the technical proficiency required to manage clusters through Prism Element and Prism Central, which are the primary interfaces for your daily operations. We will move beyond basic configuration to understand the pragmatic realities of the hybrid multi-cloud journey, ensuring you are equipped to handle production environments with confidence. By the time we conclude, you will have a deep understanding of the Nutanix solution portfolio and the specific administrative tasks necessitated by version 6.5. This course is built to bridge the gap between theoretical knowledge and the hands-on requirements found in the proctored exam environment. The roadmap for our time together is structured to mirror the practical life cycle of a Nutanix administrator. We begin with the foundational elements of storage architecture and AOS components, followed by an intensive look at virtual machine management through the AHV Hypervisor. As we progress, we will tackle critical topics like data protection, disaster recovery orchestration, and the strategic importance of lifecycle management. Each section is designed to provide you with the necessary expertise to pass the NCP-MCI exam and to effectively maintain a high-performance, secure infrastructure. You will learn how to leverage automation, monitor system health, and implement security hardening in a way that aligns with standard enterprise practices. Successfully passing the NCP-MCI version 6.5 exam requires more than just memorizing facts. It demands an intuitive grasp of how the various components within the Nutanix ecosystem interact. The exam blueprint emphasizes your ability to make sound architectural decisions within the context of AOS and the encompassing Prism dashboards. We will examine the nuances of node management, cluster expansion, and the intricacies of networking within AHV. You should approach these sessions with the intent of applying these concepts to real-world scenarios where stability and scalability are paramount. I encourage you to think critically about the trade-offs involved in cluster configuration and resource allocation throughout every session. Before we dive into the technical specifics, ensure you have a baseline understanding of virtualization concepts and basic networking, as these are the building blocks for the more advanced features we will cover later. Our focus remains on the specific implementations within the Nutanix software stack, meaning we will spend significant time on the interaction between storage containers, vDisks, and the underlying hardware. We will dissect the logic behind data reduction technologies and storage tiering to ensure you can optimize performance for diverse workloads. This comprehensive approach ensures that you are not only ready for the certification exam, but also prepared to manage a robust, production-ready Nutanix environment. I look forward to guiding you through this material. See you in the next lecture. Welcome back. Today, we are beginning our deep dive into the foundational building blocks of the Nutanix software stack. We will examine the core components and architectural principles that define the AOS 6.5 platform and make its distributed storage model possible. To understand the Nutanix platform, one must start with the controller VM, or CVM, which operates as a standard virtual machine on every host within the cluster. It abstracts the physical hardware by intercepting all storage I/O requests from the hypervisor and redirecting them to the distributed storage fabric. This fabric acts as a unified software-defined layer that manages storage across nodes, allowing the cluster to present a single pool of resources. Because the CVM runs as a guest, it remains agnostic of the underlying hypervisor, be it AHV, ESXi, or Hyper-V, ensuring a consistent operational experience. Communication between the user virtual machines and the fabric happens through a dedicated virtual switch, keeping storage traffic isolated and optimized. When an application writes data, the CVM ensures that local copies are written first to maximize performance before replicating those blocks to other nodes for resiliency. This architecture essentially turns disparate servers into a highly available, unified storage appliance that scales linearly as you add more nodes to the infrastructure. At the heart of the distributed storage fabric sits Stargate, the service responsible for the data path and all I/O operations. Stargate handles the incoming requests, determines the placement of data based on the cluster configuration, and manages the life cycle of the data blocks within the storage pool. Complementing this is Cassandra, the distributed metadata store that keeps track of where every piece of data resides across the entire cluster. Instead of relying on a single master node that could become a bottleneck, Cassandra uses a distributed ring architecture to ensure high availability and efficient querying of metadata. If you imagine a massive library where the card catalog is split among hundreds of librarians who all talk to each other, you get a sense of how Cassandra maintains consistency across the environment. This metadata management is crucial because even if an entire node fails, the cluster can quickly reconstruct the location of its data by querying the remaining nodes. Consequently, the system remains performant and resilient, preventing data loss even under significant cluster-wide hardware failure scenarios. While Stargate and Cassandra handle real-time I/O and metadata, background health and maintenance tasks are delegated to other critical components like Curator and Zookeeper. Curator functions as the cluster's internal janitor and orchestrator, running recurring scans to ensure data integrity, perform space reclamation, and manage background tasks like data redistribution after a node addition. It works tirelessly in the background to prevent fragmentation and verify that the defined replication factor is maintained across all logical storage containers. Meanwhile, Zookeeper acts as the configuration brain, managing cluster state information and handling the complex task of leader elections among services. It ensures that every node in the cluster has a consistent view of the configuration and knows which services are active or undergoing maintenance. Without this masterless coordination, the distributed nature of the cluster would quickly devolve into chaos, as individual nodes would lose synchronization regarding their defined roles or resource availability. Finally, we must look at Genesis, which provides the essential orchestration service that keeps all these aforementioned processes running. Genesis is the first service to start when a CVM boots and is responsible for managing the lifecycle of every other process, including starting, stopping, and monitoring them for crashes. If a process like Stargate or Cassandra ever hangs or fails, Genesis is the mechanism that detects this behavior and attempts to restart the service to restore functionality quickly. It provides a reliable interface for cluster management tools, essentially acting as the local control point for every node in the environment. This layered approach, where specific services manage data, metadata, coordination, and orchestration, proves why the AOS architecture is so robust and capable of supporting complex enterprise workloads without traditional hardware constraints. By separating these concerns, Nutanix ensures that a failure in one subsystem does not propagate to another, maintaining the overall stability of the cluster in diverse operational conditions. See you in the next lecture. Welcome back. Today, we are going to explore the mechanics behind managing storage containers within the Nutanix ecosystem. In the Nutanix architecture, a storage container serves as a logical abstraction of the underlying physical disk space, functioning as a fundamental construct for data placement and governance. When we view this through the lens of a shared nothing architecture, the container acts much like a folder that shares the total pool of storage resources across the entire cluster. By defining these logical boundaries, we gain the ability to enforce specific policies that dictate how our data behaves, is protected, and is consumed by hypervisors. It is essential to recognize that while storage containers are managed at the storage layer, they are essentially the entities that expose storage as NFS data stores or SMB shares to the hypervisor management interface. This decoupling of physical hardware from logical presentation is precisely what allows Nutanix to scale performance and capacity linearly without the bottlenecks typically associated with traditional storage area networks. Managing these containers effectively requires an understanding of how the underlying AOS software orchestrates I/O requests across all available nodes in the cluster. At the heart of the configuration process for any storage container is the decision regarding the replication factor, or RF, which directly dictates the resilience of the data stored within. The replication factor determines how many copies of the data are maintained across independent physical failure domains, with RF2 being the default for clusters that prioritize capacity and standard levels of availability. By choosing RF2, we guarantee that there is at least one additional copy of our data on a different node, ensuring that if a drive or a full node fails, the data remains accessible and operational. For environments requiring higher levels of fault tolerance, such as mission-critical databases or infrastructure where uptime is non-negotiable, we opt for RF3. Using RF3 forces the system to keep 3 distinct copies of the data, which inherently requires significantly more raw capacity, but provides a robust survival mechanism against multiple concurrent failures. Choosing the appropriate replication factor is always a trade-off between the desire for pure storage density and the architectural requirements for data survival in your specific deployment scenario. Closely related to this replication logic is the architectural principle of data locality, which is perhaps the most significant performance optimization in the Nutanix ecosystem. In a traditional virtualized environment, the compute and storage layers are frequently tethered by a network fabric, creating a frequent and costly path for every read and write request. Nutanix flips this paradigm by ensuring that the virtual machine's data is physically written to the local disk of the node currently running the virtual machine workload. When a VM requests data, the AOS process attempts to serve that request from the local high-performance storage on the same host, drastically reducing latency and minimizing the utilization of the physical backend network. While the system manages the movement of data behind the scenes to maintain this affinity as VMs migrate between hosts, the container acts as the scope for these locality policies. By respecting the nuances of locality during initial container design, we ensure the most efficient use of resources and the lowest possible I/O response times for our infrastructure. To implement these logical containers, we interact directly with Prism Element, which serves as the comprehensive management interface for the individual cluster. Within the storage menu, we define a container by specifying a name, selecting the appropriate storage pool if multiple exist, and setting the initial replication factor to align with our disaster recovery or availability objectives. Prism Element also provides the necessary mechanism to map these containers to the hypervisor, allowing them to be presented as either NFS exports or SMB shares depending on the specific hypervisor integration requirements. We also have the capability to handle whitelisting for external access, a feature that enhances security by ensuring only authorized nodes or clients can access the storage export. This whitelisting is a critical operational safeguard, especially in environments where we want to limit the visibility of storage mounts to specific networks or compute segments. Once the container is scoped and permissioned within Prism Element, the hypervisor can mount this storage just as it would any conventional network data store, enabling immediate VM deployment and disk provisioning. Efficient management of these containers also involves understanding how they interact with advanced features, like inline compression or erasure coding, settings configured at the container level to influence volume performance and capacity usage. When we create a container, we are not just setting a name and a size. We are establishing a policy-driven environment that dictates the life cycle of the bits stored within it. If we choose to leave compression disabled on a container housing write-heavy log databases, we avoid the CPU overhead of unnecessary processing, while enabling it for standard general-purpose servers can yield significant space savings over time. It is important to remember that these configurations are applied at the cluster granularity, but enforced through the container construct, making the container the logical unit for governance. By carefully tailoring these settings, we align the storage infrastructure's physical reality with the demanding and diverse requirements of modern enterprise applications. This deep understanding of how containers abstract and manage capacity is what allows system administrators to maintain balance and avoid the common pitfalls of resource oversubscription in scale-out environments. See you in the next lecture. Welcome back. In this chapter, we will explore how Nutanix AOS optimizes storage footprints through advanced data reduction technologies. Storage efficiency is a cornerstone of modern infrastructure management, and in this chapter, we will master the underlying mechanics of how Nutanix handles data reduction. You will learn to navigate the intricate interplay between inline and post-process compression, ensuring that your environment remains performant while minimizing footprint. We will deconstruct the Nutanix deduplication engine, examining how it functions across both performance and capacity tiers to maximize your storage investment. Understanding erasure coding, or ECX, is equally critical here. as we will break down its striping mechanics and overhead calculations to help you make informed architectural decisions. By the time we conclude, you will be proficient in applying these data reduction policies at the container level to achieve the highest possible storage ROI. Data reduction in Nutanix is not a monolithic feature, but a tiered hierarchy of logic tailored to the workload and the underlying storage medium. We begin with inline compression, which operates within the memory of the controller VM before data ever touches the disk. This mechanism is essentially transparent to the guest virtual machine, acting on writes as they land, which provides immediate space savings without significant latency penalties. However, there is a nuance when we speak about post-process compression. Unlike the inline variety, post-process compression runs as a background task, effectively cleaning up data that was not compressed during the initial write cycle. This ensures that even suboptimal data patterns are eventually condensed, maintaining a lean storage footprint over the life cycle of your virtual machines. Understanding the deduplication engine requires us to look beyond simple block matching. Nutanix implements deduplication differently depending on whether your data resides on the performance tier, which is typically your flash-based SSDs, or the capacity tier, which generally utilizes hard disk drives. On the performance tier, deduplication operates in a way that minimizes computational overhead by using a fingerprinted approach to identify duplicate data blocks before they are committed to persistent storage. Conversely, moving data to the capacity tier triggers a more aggressive examination process, as the goal shifts from raw I/O speed to maximizing density and cost efficiency. It is important to remember that these engines are designed to be cluster-aware, meaning that the deduplication process is distributed across all nodes in the cluster, preventing the controller VM from becoming a bottleneck during intensive ingestion periods. Erasure coding, or ECX, represents the most complex yet beneficial aspect of our storage efficiency strategy. At its core, ECX is a technique similar to RAID, but it is implemented at the software level with significantly more flexibility and resilience. Instead of mirroring data, which inherently requires a twofold overhead, ECX stripes data across multiple nodes and adds parity blocks. If you have an M plus P configuration, where M is the number of data segments and P is the number of parity segments, the overhead is calculated as the ratio of parity to data. While this significantly reduces the space requirements compared to traditional replication factor 2 or 3, there is a computational cost associated with calculating parity. We must balance our need for raw capacity against the processing power required to manage these parity stripes, particularly under heavy, write-intensive workloads. Configuring these features is done primarily on a per-container basis within the Prism interface. By applying these policies to a specific container, you gain the granular control necessary to match your storage efficiency features to the specific requirements of the workloads hosted within. For instance, a container hosting VDI workloads might benefit significantly from deduplication due to the repetitive nature of OS files, whereas a container hosting a SQL database might prioritize performance and disable deduplication while still utilizing compression. This per-container configuration is how we bridge the gap between abstract architectural concepts and real-world infrastructure outcomes. You must evaluate the I/O profile of your data before enabling these features, as turning on every efficiency setting indiscriminately will consume CPU cycles and increase latency, effectively trading performance for space. The decision to enable or disable these features is not a one-time configuration, but a continuous management process. Every decision to compress or deduplicate data influences the overall storage lifecycle, from initial ingestion through to long-term archiving. As you manage these environments, pay close attention to the impact on the cluster memory and CPU utilization, as the metadata required to track deduplicated blocks must reside in the memory of the controller VMs. If your metadata grows too quickly, it can impact the performance of your entire storage subsystem. This is why we monitor the data reduction ratios within Prism, ensuring that the benefits we obtain from space savings do not come at the expense of cluster stability. Constant monitoring allows you to adjust policies in real time, aligning your infrastructure with changing business needs. See you in the next lecture. Welcome back. In this session, we will examine the mechanics of Nutanix intelligent tiering and the architectural structure of vDisks within the distributed storage fabric. The foundation of the Nutanix storage architecture relies on the intelligent placement of data across heterogeneous media types, specifically NVMe, SSD, and HDD. By abstracting these physical devices into a unified pool, the distributed storage fabric ensures that data resides on the most appropriate medium based on its current access pattern. The system continuously monitors the I/O profile of every vDisk to determine whether data is currently hot, meaning it is experiencing high frequency of read and write operations, or cold, implying it has become largely static. When a vDisk is created, the fabric does not statically bind it to a single type of media, but rather treats the storage pool as a high-performance reservoir that responds dynamically to workload demands. This is fundamentally different from traditional arrays where you might manually provision specific LUNs on specific tiers of storage. By leveraging the underlying performance characteristics of NVMe and SSD versus the capacity density of HDD, Nutanix optimizes for both speed and cost efficiency without requiring administrative intervention for every data movement. Information Lifecycle Management, or ILM, is the background process responsible for this automated movement of data between tiers. The system tracks the access frequency using a weighted mechanism that pushes frequently accessed data blocks toward the fastest media tiers, such as NVMe or SSD, and migrates less accessed blocks down to the slower HDD tier. This process happens asynchronously and transparently to the virtual machines, ensuring that the performance impact on the guest operating system is minimized. Administrators often utilize the concept of flash mode for workloads that require consistent, low-latency performance that precludes the latency inherent in tiering transitions. Enabling flash mode effectively tells the system to pin data from specific vDisks or containers to the available flash storage, bypassing the standard ILM migration logic for those specific objects. While this provides predictable performance, it consumes valuable flash space that could otherwise be used for caching or accelerating other parts of the cluster, so it should be used judiciously based on performance profile requirements. The vDisk in Nutanix is not a monolithic file, but rather a logical construct composed of various extents spread across different nodes and disks within the cluster. When the distributed storage fabric manages IOPS distribution, it acknowledges that a single vDisk might be experiencing heavy read activity while another is relatively dormant. By striping the data blocks across all available nodes, the system inherently parallelizes I/O operations, which prevents the bottleneck often seen in traditional storage controller architectures. The controller virtual machine, acting on each node, ensures that the locality of data is respected whenever possible to reduce network latency during read operations. If data is requested that resides on a remote node, the cluster uses its high-speed metadata tracking to efficiently fetch the necessary extents, often creating a local cache copy if the block is read frequently enough to warrant it. This granular level of management ensures that the cluster performs as a single, cohesive entity, rather than as a collection of isolated server local disks. Understanding how these tiers interact requires a view of the storage container as the primary policy enforcement point. Within a container, you define the parameters that override or augment the default ILM behavior, providing a layer of abstraction that simplifies day-to-day operations. When a write operation occurs, it is initially ingested into the fastest available tier, typically an SSD or NVMe, to ensure the write is acknowledged as quickly as possible. Subsequent read operations draw from this top tier, but as the access frequency drops over time, the ILM process gradually moves these extents to the lower tiers to free up the valuable high-performance space. This lifecycle ensures that the cluster maintains a balance where the performance of the NVMe tier acts as a buffer for the most dynamic data, while the HDD tier serves as a large-scale repository. For an administrator, the goal is to observe the tiering efficiency through Prism to ensure that the distribution of data reflects the actual service level requirements of the hosted applications. See you in the next session. Welcome to this chapter on Prism Central, where we will examine its deployment and its critical role in unifying your multi-cloud environment. This module is essential for mastering the centralized management features that differentiate a good administrator from an expert. Prism Central serves as the operational brain of a Nutanix multi-cloud deployment, providing a unified management plane for multiple Prism element clusters. While Prism element is local to a specific cluster, handling initial configuration and day-to-day hypervisor and storage operations. Prism Central aggregates these disparate clusters into a single pane of glass. When you deploy the Prism Central virtual machine, you fundamentally change how you interact with your infrastructure, shifting from a cluster-centric view to a global resource perspective. The architecture of a Prism Central VM involves a specialized distribution of services, including the Prism Central service itself, a dedicated analytics engine, and the necessary database components to maintain configuration state. Deploying it requires you to choose between a single node setup, which is common for smaller environments, or a scale-out deployment, which ensures high availability and increased capacity for intensive monitoring tasks. Regardless of the size, the core objective is to reduce operational overhead by consolidating alerts, performance metrics, and configuration tasks across diverse geographic sites. Choosing the right license for your Prism Central instance is a strategic decision that heavily influences the operational value you extract from your infrastructure. The Prism Starter tier provides the baseline functionality required for basic cluster management, allowing you to monitor and manage your Nutanix environment through a centralized interface. However, the true power of the platform is unlocked with Prism Pro or Ultimate, which introduce sophisticated automation and advanced analytics. These tiers offer features such as capacity planning, which relies on machine learning to forecast resource exhaustion, and custom reporting capabilities that are essential for large-scale enterprise environments. With Pro or Ultimate, you also gain access to entity search, advanced performance troubleshooting, and the ability to define customized alert policies that can span multiple physical clusters simultaneously. Transitioning from the features included in the base set to these advanced tiers often allows organizations to move from reactive troubleshooting to proactive infrastructure management. Registration process is the final step in establishing a functional link between your local Prism element clusters and the central management plane. Once you have deployed the Prism Central VM, you initiate the registration process from within the Prism Element Web Console by entering the IP address of your Prism Central instance. Upon authentication, the local cluster securely transmits its inventory and performance metrics to the central service, effectively onboarding the cluster into the managed domain. This connection is not merely for observation. It is a bidirectional path that allows you to perform cross-cluster tasks directly from the global interface. Security is maintained through a robust communication protocol, ensuring that management traffic remains isolated and controlled. Once registered, the cluster appears in the global dashboard, and you can immediately begin creating policies that apply to resources running on that specific hardware, regardless of whether that hardware is sitting in your primary data center or a remote branch office. Working within this centralized framework enables administrators to manage diverse geographic sites and even public cloud resources as a cohesive entity. By utilizing the single pane of glass interface, you gain a standard operational posture that eliminates the need to switch between different browser tabs for every individual cluster. For a global organization, this means that resource monitoring, event aggregation, and lifecycle tasks, such as software updates, can be triggered and observed from one location. Furthermore, this structure allows for consistent policy enforcement across the entire stack, which is critical for compliance and maintaining identical operational standards across disparate environments. When your infrastructure scales beyond a single site, the ability to view the health of your entire estate, including public cloud integrations, becomes a necessity rather than a luxury. This centralized visibility shortens the time to resolution for performance bottlenecks, as you can quickly isolate issues that might be affecting workloads spread across different physical or logical boundaries. See you in our next technical discussion. Welcome back. In this chapter, we will walk through the precise steps required to transition a set of raw Nutanix nodes into a functional, production-ready cluster. The process of cluster initialization begins with the Foundation tool, which acts as the orchestrator for imaging nodes and deploying the controller virtual machine, or CVM, onto each physical host. Before running Foundation, you must ensure that your physical network environment is correctly configured, specifically regarding the discovery of nodes, which often happens in a flat, untagged VLAN during the initial boot phase. Foundation automates the installation of the Acropolis hypervisor and the Nutanix software stack, ensuring that the CVMs are properly provisioned with the requisite CPU and memory resources. Once the software is installed, you use the cluster initialization wizard within Prism Element to define the cluster name, which should be chosen carefully to reflect its role within your data center. The cluster virtual IP, or VIP, serves as the single point of entry for your administrative sessions, providing a stable address that remains accessible regardless of which CVM might be performing the master role for the cluster. You must also configure the iSCSI Data Services IP, which is a critical construct used by the network to manage block storage traffic effectively. Misconfiguring this address can lead to storage connectivity issues, so verifying the network routing path between your hosts and the iSCSI target is always a mandatory part of the initialization ceremony. Once the basic identity of the cluster is established, our attention must shift towards system integrity, which relies heavily on external services like NTP, DNS, and SMTP. Nutanix clusters are distributed systems, and maintaining clock synchronization across all nodes is not merely a suggestion. It is a fundamental requirement for the integrity of the underlying distributed file system. If the time drift between nodes exceeds a small margin, authentication processes, log entries, and data consistency operations will inevitably fail or report false errors. Similarly, DNS configuration is required to ensure that components can resolve host names correctly, which simplifies management and prevents issues during cross-cluster communications or software upgrades. SMTP settings are equally important because these allow the Nutanix cluster to proactively alert administrators via email about hardware failures, capacity warnings, or potential security events. When configuring these global services, always aim for high availability by specifying multiple redundant NTP and DNS servers, effectively removing single points of failure from your management infrastructure. Without these services correctly anchored, you will find it increasingly difficult to perform routine diagnostics or integrate your Nutanix environment with other enterprise solutions. In the modern enterprise landscape, software licensing and cluster hardening are tasks that define the security posture and compliance state of your infrastructure. After the initial setup, you navigate to the Nutanix support portal to generate a license file, which must then be redeemed and applied within the Prism console to unlock the full feature set corresponding to your purchased edition. Security hardening should occur immediately following deployment rather than being treated as an afterthought. This involves disabling unnecessary services on the CVMs and applying the STIG compliance templates that Nutanix provides out of the box. By integrating your cluster with Active Directory or LDAP, you move away from reliance on local Prism admin accounts, thereby allowing you to leverage centralized identity providers for all administrative access. Within the Prism interface, you should then define Role-Based Access Control, or RBAC, to enforce the principle of least privilege. This ensures that users are granted only the permissions necessary for their distinct tasks, such as VM management or storage monitoring, which drastically reduces the risk of accidental configuration drift. Taking these steps creates an environment that is not only functional, but also resilient against unauthorized access and common operational errors. I will see you in the next session. Welcome back. In this session, we will examine the mechanisms for scaling out your Nutanix environment and preserving operational integrity during hardware intervention cycles. Cluster expansion is a fundamental aspect of the Nutanix scale-out architecture, allowing administrators to grow their infrastructure linearly as demand increases. Before introducing a new node to an existing AOS cluster, thorough preparation is mandatory to ensure compatibility and stability. You must first verify that the hardware specifications of the new node align with the existing block, specifically regarding CPU, memory, and storage configurations. It is equally important to validate that the AOS version on the target node is compatible with the current cluster version to avoid potential metadata mismatches or fabric integration failures. Once physical installation is complete, the expansion workflow is managed directly through Prism Element, which automatically detects the nodes and integrates them into the cluster topology. Throughout this process, the cluster controller virtual machines, or CVMs, perform an automated handshake to join the node to the communication network. This procedure requires careful monitoring of the task status within the Prism interface to confirm that the storage pool successfully incorporates the new physical capacity without disrupting active I/O. Proper preparation reduces the risk of accidental outages during the configuration phase, as the cluster must rebalance data to maintain its redundancy factor across the newly available disks. When the operational lifecycle necessitates the removal of a node, such as during hardware decommissioning or hardware migration, graceful evacuation is critical to prevent data loss. The removal process begins by initiating a host maintenance mode request, which triggers the live migration of all resident virtual machines to other available hosts within the cluster. Once the host is successfully vacated, the underlying AOS software manages the evacuation of data from the local storage tier to the remaining nodes in the cluster. This rebalancing process consumes internal bandwidth. Therefore, it is prudent to perform this during periods of lower storage I/O density to avoid potential performance degradation for guest applications. The node removal operation also includes updating the cluster metadata to acknowledge the reduced capacity and removing the node's identity from the internal zookeeper configuration. Only after the evacuation is verified as complete should the node be physically powered down or disconnected from the backplane. This careful orchestration ensures that every protected data block is successfully mirrored or replicated to other healthy nodes, strictly adhering to the configured fault tolerance requirements of the storage container. Maintaining a hardware fleet frequently involves component-level upgrades, such as replacing failed storage media or expanding DIMM counts to address memory pressure. Nutanix simplifies these intrusive operations by leveraging maintenance mode to isolate the targeted node from standard scheduling activities. By placing a host into maintenance mode via Prism, you instruct the AHV hypervisor to live migrate existing workloads to alternate nodes, ensuring zero downtime for the virtualized operating systems. After ensuring the host is empty of VMs, hardware maintenance can proceed on the chassis, including the replacement of hot swap, solid-state drives, or non-volatile memory modules. Once the physical hardware is refreshed, the node is exited from maintenance mode, allowing the AHV scheduler to rebalance the virtual machine distribution automatically. This capability to perform infrastructure lifecycle tasks during active business hours is a significant advantage of the distributed architecture over traditional legacy systems. By automating the migration and validation steps, administrators can focus on capacity planning rather than manually orchestrating server-level changes that were previously high-risk events. See you in our next discussion. Welcome back to our journey through the Nutanix architecture, where we shift our focus toward maintaining the operational integrity of your infrastructure. In this chapter, we explore the mechanisms for proactive health monitoring and the structured reporting necessary to satisfy both technical stakeholders and management requirements. Effective infrastructure management relies on the fundamental capability to observe the state of your environment without constant manual intervention. The Prism Health dashboard serves as your primary window into the heartbeat of your Nutanix cluster, utilizing a simplified color-coded system to indicate the status of various components. A green indicator confirms that a specific subsystem is operating within normal parameters, while yellow and red signals highlight warnings or critical failures, respectively. You should treat these indicators as the first line of defense when assessing the health of hardware nodes, storage pools, or networking fabric. When a status shifts away from green, the dashboard provides contextual information that helps isolate whether the issue is transient or persistent. Relying on this visual feedback allows administrators to prioritize remediation efforts based on the severity of the alert rather than reacting to every granular log entry. By mastering this interface, you move from being a reactive administrator to a proactive engineer capable of stabilizing the environment before end users report performance degradation. Beyond simple dashboard observations, you must implement a robust alerting framework to handle conditions that require immediate attention. Nutanix allows you to configure specific alerts that trigger when system thresholds are crossed, such as high CPU utilization, memory pressure, or network latency spikes. You can route these alerts through multiple channels, including direct email notifications to your operations team or SNMP traps directed toward a centralized network monitoring platform like SolarWinds or PRTG. The critical aspect here is defining the right level of granularity for your notifications, as flooding an inbox with noisy alerts often leads to banner blindness. You should aim to configure alerts that are actionable, ensuring that each notification provides enough metadata to initiate a diagnostic workflow immediately upon receipt. Always verify the SMTP or SNMP connectivity configuration within the Prism settings to ensure that the infrastructure can successfully reach your monitoring targets during a failure event. When issues remain elusive, the Nutanix Cluster Check, commonly known as NCC, becomes your most vital diagnostic tool. NCC acts as a comprehensive health check framework that runs a series of individual checks across the entire cluster to identify latent software, metadata, or hardware issues. You can initiate these checks directly from the Prism interface for a user-friendly execution, or leverage the command line interface via SSH for more detailed output and automation capabilities. Running NCC regularly is a best practice, as it detects inconsistencies that might not yet manifest as performance degradation in the dashboard. When you execute an NCC check, the system outputs a status of success, warning, or failure for every test case, allowing you to trace the root cause of systemic instability. I strongly recommend interpreting the command line output carefully, as it often provides specific guidance on the exact physical node or service that requires intervention, which is instrumental when filing support cases with Nutanix. Finally, we must address the requirement for reporting on capacity and health for transparency, particularly for stakeholders who do not interact with the Prism web console. Custom report generation allows you to aggregate metrics over specific timeframes, providing a quantitative history of cluster consumption and availability. You should use these reports to identify trends, such as increasing storage demand or recurring hardware warnings, which help in proactive planning rather than crisis management. Whether you are generating a weekly report on cluster utilization or a summary of health events for a quarterly business review, the ability to tailor the data output is essential for demonstrating value. Understanding how to pull this data effectively means learning to group the metrics relevant to your environment while filtering out irrelevant noise. Mastery of these reporting features will ensure that you remain compliant with operational standards and provide data-driven insights that support informed decision-making within your organization. See you in the next lecture. Welcome back. In this lesson, we will focus on the fundamental aspects of managing the Acropolis hypervisor, commonly known as AHV, within your Nutanix environment. AHV is essentially a hardened version of the kernel-based virtual machine, or KVM. While it inherits the core maturity and robustness of the KVM project, Nutanix has introduced significant enhancements specifically designed to integrate the hypervisor deeply with the controller virtual machine, or CVM. When you operate an AHV host, communication between the host and the CVM occurs over a dedicated internal bridge, which ensures that storage I/O and management traffic are prioritized and isolated from general network traffic. Unlike traditional hypervisors such as ESXi or Hyper-V, which often operate as modular add-ons to a general-purpose operating system or a proprietary microkernel, AHV is optimized specifically for the Nutanix stack. This integration eliminates the overhead of managing a disparate management plane, as all hypervisor functions are exposed directly through Prism. Because the hypervisor and the storage controller are co-resident on the same physical server, the latency for storage operations is minimized significantly. Understanding this communication path is foundational before you attempt to troubleshoot any performance issues or connectivity problems between your compute and storage resources. When we compare AHV to VMware ESXi or Microsoft Hyper-V, the difference primarily lies in the philosophy of the virtualization layer. ESXi acts as a bare metal hypervisor that abstracts hardware, but it requires vCenter for anything beyond basic host-level management, which introduces a separate dependency layer. Hyper-V, meanwhile, requires a full Windows Server installation, introducing a broad attack surface and the necessity for Windows-specific patching cycles. AHV, by contrast, is stripped of unnecessary components, leaving only the essential services required to run virtualized workloads. This architecture reduces the surface area for vulnerabilities and simplifies the lifecycle management process immensely. Since there is no complex management appliance required for the hypervisor itself, you manage your compute resources using the same interface you use for your storage and networking configurations. This unified approach is what drives the operational efficiency that organizations seek when transitioning to a hyper-converged infrastructure. Managing the host configuration securely is a non-negotiable requirement in modern data centers, and Nutanix provides the Security Configuration Management Automation, or SCMA, toolset. SCMA constantly monitors the AHV host configuration to ensure that it adheres to predefined security profiles, such as those derived from STIGs or CIS benchmarks. If an administrator inadvertently changes a configuration setting that deviates from the approved policy, the SCMA system automatically detects the drift and reverts the setting to the secure baseline. This automation removes the human element of manual checking and ensures that compliance is not just a point-in-time assessment, but a continuous state of operation. Beyond security, you must also be mindful of the hypervisor lifecycle, which is handled through the integrated lifecycle management tools in Prism. These tools automate the orchestration of updates for both the hypervisor and the underlying firmware, ensuring that your host is always running on a supported and stable version without requiring manual intervention during the patching process. Effectively managing AHV requires a shift in perspective if you are accustomed to traditional hypervisors where storage abstraction layers often isolate the server administrator from the storage performance metrics. In the Nutanix environment, the AHV host is an active participant in the entire storage fabric. You should treat the host not just as a container for virtual machines, but as a balanced data node. Best practices dictate that you monitor the health of the internal bridges and verify that the virtual network interfaces are correctly mapped to your physical uplinks to avoid traffic bottlenecks. Regularly reviewing your host logs through the standard Prism interface is sufficient for most operations, as the system centralizes all critical errors across the cluster. By maintaining a clean configuration and leveraging the automated reporting capabilities of the cluster, you minimize the risk of environmental instability. Consistent attention to these operational details ensures that your virtualization layer remains performant, secure, and ready for whatever workload requirements your organization demands. See you in the next lesson. Welcome back. In this chapter, we will explore the comprehensive lifecycle management of virtual machines within the AHV environment, focusing on their configuration and operational maintenance. In this chapter, we explore how to effectively handle virtual machines within an AHV environment, covering everything from initial provisioning to retirement. By mastering the core lifecycle operations, you ensure that your infrastructure remains both agile and performant for your various guest workloads. Understanding these mechanics is a fundamental requirement for anyone aiming for the NCP-MCI certification, as it bridges the gap between architectural theory and practical daily administration. We will examine how virtual hardware is abstracted and managed through the Nutanix interface to provide consistent performance across your cluster. This knowledge will empower you to move beyond simple deployments into sophisticated, policy-driven cloud management. Managing a virtual machine lifecycle starts with the image service, which acts as a centralized repository for ISO files and raw disk images. Instead of manually uploading installers to individual hosts, you house these images in the image service, making them accessible to any node within your Prism managed cluster. When you define a new virtual machine, you designate the resources, such as the number of virtual CPUs and the amount of memory, which the AHV hypervisor then carves out from the physical host pools. A critical aspect of this configuration involves selecting the appropriate disk controller, such as SCSI, IDE, or SATA, depending on the guest operating system requirements and performance expectations. SCSI controllers are generally preferred for data-intensive workloads due to their superior efficiency in handling concurrently queued commands. You must also consider the interaction between the virtual guest and the underlying AHV storage fabric, ensuring that the integration is seamless and stable. A cornerstone of achieving high-performance virtualization in Nutanix is the correct deployment and management of Nutanix VirtIO drivers. These para-virtualized drivers provide an optimized path for guest operating systems to communicate directly with the underlying hypervisor hardware, effectively bypassing the overhead associated with emulated devices. When dealing with Windows guests, you must plan for the injection or installation of these drivers during the provisioning process, as they are not native to the standard Windows installation media. For Linux environments, modern distributions contain the VirtuoNet or Virtio BLK drivers in the kernel, but you must still verify that your specific kernel supports the features required by the AHV environment. Failing to load these drivers will force the VM to rely on legacy emulation, which results in significant latency and degraded throughput for both networking and disk I/O operations. Always treat the guest tools as a primary integration point to enable not just driver functionality, but also graceful shutdowns and detailed monitoring. Beyond the initial setup, you will often find yourself needing to perform operational tasks, such as taking snapshots or executing power transitions. Snapshots in Nutanix are metadata efficient, allowing you to capture the state of a virtual machine at a specific point in time without the performance penalty associated with traditional deep copy snapshots. These snapshots are integrated into the data protection workflow, providing a safety net before you perform risky updates or configuration changes on your guest systems. When administrative needs require a more programmatic approach, you can leverage the Acropolis Command Line Interface, or ACLI, to perform these operations with precision. Whether you are using the graphical interface provided by Prism to perform a quick reboot or scriptable commands via ACLI to manage thousands of devices, the underlying logic of the AHV object model remains the same. You are essentially interacting with an API that translates your requests into logical volume operations performed by the distributed storage layer. The final stage of the lifecycle is the deletion or migration of the virtual machine, which must be handled with care to prevent orphan data or wasted storage resources. When you delete a virtual machine via Prism, the associated virtual disks, or vDisks, can be removed from the target storage containers, reclaiming space immediately for other workloads. It is important to confirm that any external dependencies, such as specific network configurations or persistent disk mappings, are properly addressed prior to dismantling the guest. By strictly following these procedures, you maintain a clean and reliable environment that is prepared for future scaling or automated orchestration. These management skills represent the daily work of a data center administrator and are tested extensively within the exam context. You now have the necessary background to start applying these configuration patterns to your specific infrastructure nodes. I will see you in the next lecture. Welcome back. In this lesson, we will explore the mechanisms behind VM templates and the operational efficiency gained through rapid cloning within the Nutanix ecosystem. Managing a virtualized infrastructure effectively requires moving beyond the manual creation of individual virtual machines. When you find yourself deploying the same operating system configuration repeatedly, the manual approach becomes a liability that introduces human error and inconsistencies. Nutanix addresses this by introducing the concept of a gold image, which acts as a master copy stored within the Prism Central VM library. By maintaining a single source of truth for your workloads, you ensure that every deployment starts from a known, secure, and pre-configured state. This workflow is central to scaling operations because it decouples the base infrastructure requirements from the specific application roles assigned to a guest OS. Once a virtual machine is perfected, you convert it into a template, effectively locking its state so that it can serve as a read-only progenitor for future instances. The actual act of cloning in Nutanix is far more sophisticated than a simple file-level copy of a virtual disk. When we initiate a clone, we leverage an architectural feature that is fundamentally designed for performance, the metadata-only or fast clone operation. In a standard storage environment, cloning a large disk would involve a linear time cost proportional to the size of the data, which is unacceptable in enterprise environments. Within the Nutanix AOS architecture, when a VM is cloned, the system tracks the vDisk mapping at the extent level without needing to duplicate the underlying data blocks immediately. Because of the unified nature of our storage fabric, these clones effectively point to the same original extents until a write operation occurs on the new VM. This technique, similar to copy-on-write mechanisms, allows you to spin up dozens of identical virtual machines in seconds, regardless of their disk size. While the ability to deploy machines rapidly is a benefit, it introduces the challenge of guest OS identity. If you clone a machine and boot it, you end up with multiple instances sharing the same hostname, IP address, and security identifiers, which will inevitably cause network conflicts. To resolve this, we leverage automatic customization tools such as sysprep for Windows environments or cloud-init for Linux distributions. During the deployment process within Prism, you provide a customization script that the new VM interprets upon its first boot sequence. This script automates tasks like resetting the machine's GUID, generating a new computer name, and triggering DHCP requests or injecting static network configurations. By integrating these scripts, the process of going from a template to a production-ready, uniquely identified server becomes a completely automated, repeatable operation. In Prism Central, the VM library serves as the centralized repository for these templates, facilitating consistent image management across all managed clusters. When team members deploy a virtual machine, they select a template from this library, ensuring that the versioning remains strictly controlled. You should think of this library not just as a storage bucket, but as a governance tool that prevents configuration drift across your multi-cloud environment. Ensuring that your gold images are patched and hardened before they reach the library is a critical security step that pays dividends in later lifecycle operations. If you discover a vulnerability, you simply update the base image, convert the updated VM back into a template, and deprecate the old one. This lifecycle management ensures that your infrastructure is as agile as the applications it hosts, maintaining high performance during deployment and consistency once the VMs are live. See you in the next lecture. Welcome back. Today we will unravel the architecture of AHV networking, starting with the Open vSwitch, often referred to as OVS, which serves as the fundamental software-defined networking component on every Nutanix node. In a standard AHV deployment, the Open vSwitch acts as the primary virtual bridge, named BR0, which manages the communication between virtual machines and the physical network infrastructure. Each AHV node utilizes this bridge to connect internal virtual interfaces to the physical uplinks available on the host. When you create a virtual network, you are essentially defining a logical segment that the OVS bridges across your cluster, ensuring that traffic flows efficiently between compute resources. The configuration of this bridge is abstracted away from complex manual commands, as Prism and command line tools like AHV provide a clean interface to manipulate these virtual switches. It is vital to understand that this bridge is not merely a transparent hub, but an intelligent gateway capable of performing frame switching based on standard IEEE 802.1q tagging principles. By abstracting the hardware layer, AHV allows the hypervisor to treat physical network ports as a single pool of resources, facilitating a consistent networking experience regardless of the underlying vendor-specific network card hardware. This architectural decision places the control logic securely inside the hypervisor, allowing for rapid deployment and modification of network topologies without the need to physically rewire server racks. Consequently, the stability of your entire virtualization stack is heavily dependent on how effectively you tune and manage this OVS bridge layer to match your existing data center network configuration. To facilitate high availability and increased bandwidth, AHV nodes aggregate multiple physical network interfaces into what is known as a bond. The bond configuration dictates how traffic is distributed across available physical ports, and choosing the right load balancing mode is a critical design decision for any administrator. The simplest mode is active backup, where one physical interface is active while the others remain in a standby state, providing basic redundancy should the primary link fail. For more demanding environments, we often turn to Balance SLB, which distributes traffic based on the source MAC address and virtual port, effectively utilizing the bandwidth of all active links without requiring special switch configuration. If your upstream physical switches support link aggregation, you might opt for LACP, also known as Active TCP, which uses a hash-based mechanism to pin traffic flows to specific physical ports. It is important to note that LACP requires precise coordination with the upstream physical switch, as it needs to be configured in an 802.3 add port channel to establish the logical link correctly. Selecting the wrong bonding mode can lead to unpredictable packet loss or connectivity issues that are remarkably difficult to debug in a production environment. Therefore, you must align your bonding strategy not only with your performance requirements, but also with the capabilities and existing architecture of your physical data center switching fabric. Traffic isolation within the AHV environment is primarily achieved through the implementation of VLAN tagging at the network and host levels. When you configure a virtual network in Prism, you assign a specific VLAN ID, which causes the OVS to tag all incoming traffic from virtual machines before it exits the physical switch. This tagging ensures that data packets remain confined to their intended broadcast domains, preventing unauthorized crosstalk between different application tiers or network segments. At the host level, the bond is configured to handle these tags, ensuring that the physical switch receives frames with the appropriate 802.1q headers. If you fail to configure these VLANs correctly on your upstream physical switches, the affected virtual machines will effectively be isolated from any network communication, leading to immediate service disruption. It is a common misconception that AHV handles all tagging automatically. While the management plane is simplified, you are still required to ensure that the physical switch ports are configured as trunks to pass all necessary VLAN tags. Properly implemented, this tagging strategy provides a robust foundation for secure multi-tenancy and traffic segmentation, which are essential in modern, high-density virtualized environments. Effective management of the AHV network stack requires a disciplined approach to bridge configuration, bonding strategies, and VLAN isolation. By mastering these core components, you ensure that your infrastructure remains both resilient and performant under various workload conditions. I will see you in the next lecture. Welcome back. Let's explore the technical nuances of advanced network configuration within the Nutanix AHV environment to optimize your infrastructure. In this chapter, we focus on moving beyond basic connectivity to achieve a resilient, automated, and observable network architecture. Achieving deep integration between your virtual environment and the physical fabric requires a firm grasp of how AOS governs traffic. We will look at how IP address management, or IPAM, reduces the administrative burden of manual static assignments by automating address allocation at the virtual network level. By defining internal networks with specific VLAN IDs, you create isolated broadcast domains that adhere to your enterprise segmentation strategy. Furthermore, we must address the management of the virtual switch, which acts as the critical bridge for all intranode and external communication. Understanding these sophisticated configurations is essential for any administrator tasked with maintaining high-performance multi-cloud infrastructure. Effective network design begins with the logical abstraction provided by the virtual switch. In AOS 6.5, the virtual switch handles the traffic flow between virtual machine instances and the physical network interface cards. When you provision virtual networks, you are essentially defining a VLAN tagged layer 2 segment that the hypervisor enforces. To implement IPAM, you define a network pool within AHV that assigns IP addresses, default gateways, and DNS servers to virtual machines as they are attached to that network. This automation ensures that IP conflict and manual entry errors are mitigated during the provisioning phase of your virtual machine lifecycle. You must ensure that the IP subnet ranges defined in the AHV network match your physical infrastructure's routing capability to allow for proper upstream connectivity. Observation is just as vital as configuration, which is where Prism Network Visualization becomes indispensable. This tool allows you to map VM virtual NICs directly to the specific physical switch ports on your top-of-rack switches. By using Link Layer Discovery Protocol, or LLDP, AHV automatically detects the connected physical hardware and displays the topology within the Prism interface. This visibility is helpful when troubleshooting physical layer issues. As 5, you can correlate high latency or packet loss with a specific physical interface. If you see a mismatch between the expected physical port and the one reported by the hypervisor, you are likely dealing with a physical cabling configuration error. Reliable network monitoring relies on this visual chain of custody from the VM kernel all the way to the physical uplink. When global throughput and redundancy requirements exceed default configurations, we turn to the command line interface, specifically the Manage VMs utility. This tool provides the low-level control necessary to modify Open vSwitch parameters, such as configuring bond modes or adjusting MTU sizes across your hosts. For instance, if your workload requires high bandwidth traffic, such as large database migrations, you might adjust the bond mode to balance traffic distribution across all active physical uplinks. The Manage VMs command allows for the implementation of LACP, or Link Aggregation Control Protocol, which requires corresponding configuration on your physical switches. You must be precise with these command line changes, as improper settings can lead to host isolation from the management network. Always validate connectivity after applying these parameters to ensure the link state remains stable and performant. Achieving an optimal network architecture is a matter of layering these components correctly. By combining the automated efficiency of IPAM with the logical isolation provided by VLANs and the granular tuning available through the Manage VMs utility, you build a sustainable foundation. The goal is to maximize the utility of your available bandwidth while reducing the overhead required for routine maintenance tasks. As your virtual landscape grows in complexity, these advanced techniques allow you to maintain visibility and control without sacrificing agility. These configurations form the backbone of a performant AHV deployment and will serve you well during the comprehensive assessment of your network health. I trust that these technical details clarify the mechanisms of advanced network operations. See you in the next lecture. Welcome back to our exploration of the Nutanix ecosystem, where today we focus on the mechanics of resiliency and workload mobility. We will examine how AHV handles host failures and maintains performance through intelligent resource balancing. Nutanix AHV High Availability, or HA, acts as a primary safety net for your virtualized environment. When a host failure occurs, the cluster immediately attempts to restart the affected virtual machines on the remaining healthy nodes. The success of this operation depends heavily on the configured HA policy, which is either best effort or reserved segment. In the best effort model, the system assumes that sufficient resources will be available across the cluster to accommodate the restarted workloads, prioritizing capacity usage until physical limits are reached. Conversely, the reserved segment policy explicitly sets aside a portion of total cluster memory and CPU, equal to the capacity of the largest host, to ensure that resources are guaranteed during a failover event. This choice between potential density and absolute availability is a fundamental design decision that administrators must make based on their specific workload requirements and risk tolerance. Regardless of the chosen policy, the cluster continuously monitors the health of each node through a heartbeat mechanism that triggers failure detection when a host stops communicating with the rest of the cluster. Effective recovery also relies on the concept of VM restart priority, which dictates the order in which virtual machines are recovered after a host failure. We can assign specific priority levels to VMs such as default, low, or high, ensuring that critical services resume operations before secondary or non-essential virtual machines. Host failure detection is designed to be efficient, identifying unresponsive nodes while avoiding unnecessary failover events caused by transient network disruptions. Once a node is confirmed as failed, the HA process initiates a reboot of the affected VMs on available hosts where memory and CPU overheads allow. This process is seamless for the infrastructure, but requires a well-planned capacity strategy to prevent resource contention during the post-failover period. By understanding how the cluster detects failure and how it prioritizes recovery, you gain the ability to proactively design more resilient virtualized infrastructures that can withstand the loss of hardware without sacrificing service uptime. Beyond resiliency, the movement of workloads is equally critical, and this is where live migration becomes essential. Live migration allows for the transparent relocation of a running VM from one host to another without interrupting user access or network connectivity. The mechanics involve a multi-step process where the memory state of the VM is transferred from the source host to the destination host, while the VM continues to operate. Nutanix utilizes an iterative memory page transfer process, where the hypervisor copies memory pages in cycles, progressively narrowing down the data that is changed during the transfer. Once the discrepancy between the source and destination is sufficiently small, the system performs a final switchover, suspending the VM for a very short duration to copy the remaining state. After this handoff, the VM resumes execution on the target node, and the source memory is cleared, completing the migration efficiently. To supplement manual migrations and manual balancing, we utilize Acropolis Dynamic Scheduling, or ADS. ADS is an automated scheduler that continuously monitors the usage of resources like CPU, memory, and storage across the cluster to prevent performance hotspots. When a host experiences sustained resource stress that degrades performance, ADS identifies the most suitable alternative host in the cluster and triggers a live migration to balance the load. This mechanism works silently in the background, making autonomous decisions to ensure that no single host becomes a bottleneck that affects multiple virtual machines. It is important to remember that ADS respects the constraints of your HA policies and anti-affinity rules, ensuring that performance optimization does not come at the cost of your availability posture. By leveraging these intelligent scheduling features, you can achieve a self-optimizing environment that requires minimal manual intervention to maintain peak cluster performance. See you in the next lecture. Welcome back. Today we are going to explore the mechanics behind software-defined security and how microsegmentation functions within the Nutanix ecosystem. In traditional data center environments, perimeter firewalls handle north-south traffic, yet east-west traffic often remains vulnerable once an intruder breaches the boundary. Flow addresses this by implementing a distributed firewall architecture directly at the virtual network interface card level of every virtual machine. Because this security logic is deeply integrated into the AHV hypervisor and orchestrated through Prism Central, you do not need to hairpin traffic to external inspection appliances. Instead, the hypervisor itself enforces granular security policies that follow the workload regardless of where it lives or migrates within the cluster. This design fundamentally shifts the security model from network-centric to workload-centric. allowing you to define policies based on the identity of the virtual machine rather than fixed IP addresses or VLAN assignments. By decoupling identity from network topology, you gain significant flexibility in managing security postures across highly dynamic virtual infrastructures. When we transition to implementing microsegmentation, the flow visualization tool becomes your most valuable asset during the planning phase. Before you create any restrictive policies, you should enable this tool to observe and map the actual communication patterns between your virtual machine tiers. The tool provides a visual representation of the active flows, helping you identify legitimate interactions and potential anomalies that require attention. It essentially removes the guesswork from rule creation by highlighting exactly which services communicate with each other over specific ports and protocols. Once you have validated these traffic patterns, you can confidently turn these observations into explicit security policies without the risk of breaking critical application dependencies. This data-driven approach to security ensures that your policies are effective and lean, avoiding the complexity associated with maintaining massive, unmanageable lists of legacy firewall rules. Application security policies, isolation policies, and quarantine rules represent the three primary constructs you will utilize within Prism Central to control traffic. Application security policies allow you to define a logical security boundary around a specific set of workloads, permitting only authorized traffic while blocking everything else by default. If you need to ensure that two environments never communicate, even if they share the same underlying network segment, you would deploy an isolation policy to enforce that separation. Furthermore, the quarantine capability provides an immediate response mechanism for compromised virtual machines by isolating them from the network while maintaining access for administrative forensic analysis. Because these policies are enforced by the distributed firewall in every node, they provide a consistent security posture that is inherently resilient against manual configuration errors or changes in the underlying physical network topology. Managing these constructs through Prism Central provides a centralized, single pane of glass, ensuring that your security intent is applied consistently across your entire Nutanix deployment. See you in the next lecture. Welcome back. In this chapter, we will master Prism Pro and Ultimate features to shift from reactive management to proactive infrastructure capacity planning. Prism Pro introduces a sophisticated layer of intelligence to your Nutanix environment by shifting the focus from simple resource monitoring to predictive capacity planning. When managing a complex multi-cloud infrastructure, it is rarely enough to know how much memory or CPU you are currently utilizing. The real value lies in understanding the trajectory of those resources. The core concept here is the runway, which acts as a temporal projection based on your historical resource consumption patterns. By analyzing your storage, CPU, and memory trends, Prism Pro calculates how many days remain before specific resources are exhausted. This allows administrators to move away from constant firefighting and instead plan hardware expansions well in advance of a critical bottleneck. If your storage utilization is growing at a steady pace, the runway engine alerts you to impending saturation point long before the file system enters a read-only state. This feature is fundamental for maintaining the uptime and performance consistency required in production enterprise environments. Beyond mere trend analysis, the what-if scenario engine provides a sandbox for your infrastructure planning. Instead of guessing how a new database cluster or a batch of virtual machines will impact your environment, you can model these workloads directly within Prism. These simulations take your actual current environment as the baseline and allow you to overlay projected workloads to see exactly how they influence your remaining runway. You might simulate the addition of 5 nodes to a cluster or the migration of a specific set of virtual machines from a legacy platform to your Nutanix environment. The engine uses your historical data to calculate the resulting infrastructure strain, effectively answering whether your current configuration can support these additions without compromising existing service levels. This capability transforms capacity planning from a speculative exercise into a data-driven process that minimizes the risk of over-allocating or under-provisioning your physical hardware. The XFit engine serves as the analytical brain behind these insights, utilizing machine learning to improve the accuracy of predictions over time. Unlike static thresholds that often trigger false positives, XFit looks at patterns and seasonal behaviors within your workloads to identify true anomalies. While runway calculations help you look forward, XFit is equally vital for looking at current efficiency through right-sizing recommendations. It identifies virtual machines that are over-provisioned, where resources are allocated but rarely used, as well as machines that are experiencing resource contention. By reclaiming idle CPU and memory from underutilized virtual machines, you effectively increase the total density of your cluster without spending a dime on additional hardware. These insights help maintain a high performance-to-cost ratio throughout the lifecycle of your virtual machines, ensuring that your Nutanix environment remains lean and highly efficient. Integrating these practices into your regular operational maintenance cycle significantly reduces the complexity of managing multi-cloud resources. You are no longer reacting to alarms, but proactively architecting your infrastructure based on empirical evidence. Whenever you see a trend indicating a potential resource conflict, the system provides clear, actionable steps to remediate the situation. Whether that means scaling out by adding nodes or right-sizing VMs to defer a capital expenditure, the visibility into your runway gives you the authority to make those decisions confidently. As we progress, keep in mind that the accuracy of these predictive models relies heavily on the quality and duration of the data collected by Prism Central. Ensuring the health of this collection process is a prerequisite for any meaningful capacity management strategy. See you in the next lecture. Welcome to the chapter on data protection, where we will examine the mechanisms Nutanix provides to ensure business continuity and reliable system recovery. This section is essential for mastering the nuances of architectural resiliency required for your certification. In the context of modern data center infrastructure, we must first address the foundational metrics that define our recovery strategy. The Recovery Point Objective, or RPO, represents the maximum tolerable period in which data might be lost from an IT service due to a major incident. Conversely, the Recovery Time Objective, or RTO, defines the targeted duration of time and a service level within which a business process must be restored after a disaster. Balancing these two objectives is an architectural trade-off that typically influences our choice of replication frequency and synchronization methods. It is helpful to view these metrics not merely as administrative checkboxes, but as the primary constraints that dictate your entire replication topology. If your business requirements mandate an RPO of near zero, you will inevitably look towards synchronous replication, which introduces different considerations regarding network latency and distance between physical clusters. We are essentially building a safety net that protects the integrity of our workloads against various failure scenarios, ranging from individual disk corruption to complete data center outages. The engine behind Nutanix data protection is the redirect on write, or RODUB, snapshot mechanism. Unlike traditional copy-on-write approaches that require multiple I/O operations to update a single metadata pointer, RODUB operates by simply pointing to the new data location while maintaining the original data blocks as immutable snapshots. This architecture eliminates the performance penalty commonly associated with taking a snapshot, as it avoids the read-before-write overhead that frequently degrades virtualization performance. When we initiate a snapshot, the system maps the existing vDisk metadata to existing blocks, and new writes are directed to fresh locations, ensuring that the original state remains consistent and untouched. From a practical standpoint, this means that you can maintain numerous snapshots of a virtual machine with virtually no impact on production performance. This technical elegance is a hallmark of the AOS file system, which treats snapshots as first-class, lightweight citizens within the storage fabric. Once we grasp the efficiency of our snapshot mechanism, we should differentiate between crash-consistent and application-consistent outcomes. A crash-consistent snapshot is essentially equivalent to pulling the power plug on a server, meaning that data in transit within the memory of an application may not be fully committed to the virtual disk. While this is often acceptable for basic storage recovery, mission-critical databases usually require application-consistent snapshots to ensure data integrity upon restoration. This is where Nutanix Guest Tools, or NGT, proves its value by facilitating the necessary interaction between the storage layer and the guest operating system. When NGT is present, it interacts with the volume shadow copy service on Windows or equivalent frameworks on Linux to quiesce application I/O and flush caches before the snapshot is formally finalized. By ensuring that the file system is in a stable state during the snapshot process, we guarantee that the backup provides a reliable recovery point that does not require lengthy integrity checks during a reboot. Effective data protection requires a rigorous assessment of both local and remote recovery needs. Local snapshots serve as our primary defense, offering rapid recovery from accidental file deletion or faulty software updates. Remote replication, which involves the transfer of this data to a secondary or tertiary site, provides the necessary protection against catastrophic site-level failures. These mechanisms together form the backbone of a comprehensive disaster recovery plan, allowing us to orchestrate failover operations with confidence. By systematically aligning your recovery objectives with the capabilities of the Nutanix storage layer, you ensure that the infrastructure remains both resilient and performant. Understanding the interplay between these components allows you to design solutions that are technically sound and operationally manageable. I look forward to discussing the intricacies of replication schedules in the next lecture. Welcome to this exploration of data protection mechanics within the Nutanix ecosystem. We are going to examine the implementation of protection domains and the surrounding scheduling policies necessary for robust recovery. At the core of an effective disaster recovery strategy in a Nutanix cluster lies the protection domain. Conceptually, you can view a protection domain as a logical container that groups together specific virtual machines or volume groups to manage their lifecycle as a single unit. When you isolate these entities, you establish a boundary that dictates how snapshots are taken, where they are replicated, and how long they persist. This separation is particularly useful in complex environments where different applications carry varying recovery point objectives or performance requirements. By decoupling protection policies from the underlying physical hardware, Nutanix allows you to manage data integrity without worrying about the specifics of the storage nodes themselves. The primary administrative tool for these operations is Prism Element, where the workflow is designed to remain consistent regardless of the scale of your virtual machine deployment. When we approach the task of creating these domains, we must pay close attention to consistency groups. A consistency group is a subset within your protection domain that defines the exact order and grouping of virtual disks that must be snapshotted simultaneously. This is indispensable for multi-tier applications, such as a database server coupled with an application server where data integrity across the entire stack is paramount. If you fail to include both tiers in the same consistency group, you might end up with crash-consistent snapshots that cannot be restored together, leading to data corruption or service failure. Nutanix handles the orchestration of these snapshots across the nodes, ensuring that the I/O flow is temporarily quieted to capture an atomic state. You define these groups through the Data Protection Dashboard, which provides a visual audit of which virtual machines are assigned to which domain. Setting up the snapshot schedule involves defining the frequency and retention policy that aligns with your business continuity plans. In Prism Element, you select a protection domain and configure a schedule that determines how often Nutanix captures the state of your protected entities. These are essentially point-in-time recovery points that leverage the underlying redirect on-write storage architecture to minimize performance overhead. You must also establish a retention policy, which explicitly dictates how many snapshots you keep locally before the system discards the oldest ones to reclaim space. Misconfiguring these settings is a common cause of unexpected storage exhaustion, so it is vital to balance the need for granular recovery points against the storage capacity available on your cluster. Always monitor the snapshot count for each domain to ensure that your actual usage does not drift away from your documented design. Monitoring these domains requires active engagement with the reporting features within Prism to ensure that your schedules are executing as expected. Problems often manifest subtly, such as a failed snapshot task or a timing issue caused by network latency during the synchronization process. Because Nutanix integrates these recovery capabilities directly into the fabric, you have access to detailed logs that clarify if any specific virtual machine is delaying the snapshot process due to high I/O wait times. Modifying a protection domain is a straightforward administrative action, but you must consider that changing a policy might affect the existing snapshot chain, potentially triggering a full synchronization if the remote site settings are altered inappropriately. Maintaining a disciplined approach to these configurations guarantees that your recovery objectives are met reliably and predictably in a disaster scenario. Until then, I hope this provides a clear framework for your studies. I will see you in the next installment. Welcome back. let us discuss how to implement robust remote replication strategies for long-distance disaster recovery within the Nutanix ecosystem. When we approach disaster recovery over significant physical distances, latency becomes the primary architectural constraint that dictates our choice of replication mode. Asynchronous replication is the standard industry approach for these long-distance scenarios because it decouples the primary site performance from the acknowledgement latency of the remote site. By setting a recovery point, objective greater than 60 minutes, we allow the system to batch and transmit changes periodically, rather than forcing a synchronous write path. This design choice effectively shields your production applications from network jitter or high round-trip time values that would otherwise stall local input and output operations. We configure these remote sites by explicitly defining the target IP address, which ensures traffic is routed correctly across your wide area network infrastructure. Establishing trust relationships between clusters is a prerequisite for this communication, as it ensures that data is encrypted in transit and that only authorized clusters can exchange replication streams. You should think of this as an explicit handshake between two distinct administrative domains that must agree on identity and capability before a single block of data is moved. Managing the flow of traffic requires a clear understanding of both outbound streams from the source and inbound acceptance at the destination. You must ensure that the underlying physical network links provide sufficient bandwidth to handle the snapshot delta changes within your configured RPO window. Otherwise, the system will fall into a state of replication lag. Prism provides the visibility required to monitor this health, allowing you to track the progress of ongoing replications via the data protection dashboard. If you observe that the snapshot transfer frequently exceeds the scheduled window, you may need to evaluate your data change rates or provision larger storage pipes between the sites. During the initial deployment of a replication schedule for massive datasets, you might encounter bandwidth limitations that make an over-the-wire transfer impractical. This is where the concept of seeding becomes invaluable, as it involves manually transporting an initial baseline copy of the data to the destination, often via a physical data mover. Once that baseline is established at the remote site, you register it with the cluster, and subsequent replication operations only need to synchronize the incremental changes. This drastically reduces the time required to achieve a state of readiness and minimizes the total window during which your primary data is unprotected. Effective monitoring revolves around the data protection dashboard in Prism, which serves as your primary control center for verifying that the replication chain remains intact. You should regularly audit the status of your protection domains to ensure that the last successful snapshot time aligns with your business continuity requirements. If a replication failure occurs, the dashboard displays clear alerts detailing the failure mode, whether it relates to network connectivity, cluster authentication, or insufficient storage capacity at the target location. Because asynchronous replication is a continuous process, failing to remediate an alert immediately can lead to an accumulation of snapshots that consumes extra storage space on both ends of the connection. Keep in mind that consistent maintenance of these remote bridges is as important as the initial configuration phase. By keeping your cluster software versions compatible and regularly testing the recovery flow, you ensure that the remote infrastructure is not just a repository for data, but a functional site that can sustain your workloads in a disaster scenario. This systematic approach to replication management mitigates the risks associated with hardware failure or site-wide outages that otherwise threaten your organizational data integrity. We'll see you in the next lecture. Welcome back. In this lecture, we examine the mechanics of high-frequency data replication, specifically near-sync and synchronous strategies within the Nutanix ecosystem. Near-sync replication is an evolution of standard asynchronous snapshots designed to meet recovery point objectives as low as 1 minute. Traditional asynchronous replication relies on snapshot schedules that, by design, incur higher latency between data copies. To bridge this gap, Nutanix utilizes lightweight snapshot technology, often referred to as LWS. Unlike standard snapshots that can be resource-intensive, LWS minimizes the overhead on the storage controller by tracking metadata changes more efficiently. This allows the system to take snapshots much more frequently without negatively impacting the performance of the production workload. When you configure a protection policy for near sync, the system orchestrates the transfer of these incremental changes to the target cluster in rapid succession. It is critical to ensure that both the bandwidth and the background I/O requirements are satisfied to maintain the consistency of these frequent snapshots. If the network becomes a bottleneck, the replication schedule may drift, which effectively negates the benefits of the intended RPO. While near-sync targets extremely low RPOs, synchronous replication aims for an RPO of 0, effectively meaning no data loss during a disaster scenario. This implementation generally manifests as metro availability, which requires a specific set of architectural constraints on your infrastructure. The most significant requirement is the round-trip time between the two sites, which must remain below 5 milliseconds to ensure that write acknowledgement times do not stall applications. Because every write operation must be acknowledged by both clusters before the guest VM receives a success signal, network topology is the primary determinant of system stability. You configure this at the storage container level, mapping them specifically between two distinct clusters. Both environments must be configured to support the shared data span, effectively appearing as a single storage entity to the hypervisors involved. When you map these containers, ensure that all networking path redundancy is thoroughly tested before introducing production traffic into the stretched configuration. Automated failover in a synchronous configuration relies on a witness VM, which acts as an independent arbiter to prevent split-brain scenarios. In a standard two-node or two-cluster site setup, it is impossible for the clusters to determine if a peer has failed or if just the network connection between them has severed. The witness VM sits in a third, independent fault domain and continuously monitors the health of both participating sites. If the primary site becomes unreachable, the witness communicates with the secondary site to coordinate a graceful transition, ensuring that only one cluster holds the mastership of the data. Without the witness, you are restricted to manual intervention, which involves human operators actively promoting the secondary site. This manual approach is prone to delays and errors that are largely unacceptable in high availability environments designed to maintain near-instant recovery. Always verify that the management network for the witness VM is separate from the physical data replication network to prevent a single point of failure from compromising the arbitration process. Configuring these replication modes requires a clear understanding of the underlying storage containers and the cluster-wide settings. For synchronous replication, storage containers must be created with the same name on both sides and appropriately mapped via the Prism interface. You must also ensure that the cluster software versions are compatible, as mismatched AOS versions can lead to inconsistencies during the synchronization process. In high availability designs, the storage container attributes, such as deduplication and compression ratios, should be consistent across sites to avoid unexpected capacity utilization spikes after a failover event. Always monitor the latency metrics within Prism as you deploy these configurations to ensure they remain well within the operational thresholds. While the technology provides robust disaster recovery, its success is fundamentally driven by the quality of the dedicated inter-site network links. By aligning your hardware capabilities with these specific protection policies, you create a resilient architecture that supports the most stringent business continuity requirements. See you in the next lecture. Welcome to our deep dive into disaster recovery orchestration, where we will translate conceptual replication into functional business continuity. We are specifically focusing on the capabilities of Nutanix Leap managed via Prism Central. When we discuss disaster recovery orchestration, we are essentially moving beyond mere data replication into the realm of service availability. While it is certainly useful to have a copy of your bits and bytes on a remote cluster, those bits remain effectively inert until a strategy for orchestration brings them to life in the correct sequence. Nutanix Leap acts as the control plane for this coordination, allowing administrators to define recovery plans that handle the intricacies of complex multi-tier applications. Without these plans, a recovery event often becomes a manual, error-prone coordination exercise that rarely meets the aggressive recovery time objective targets set by modern stakeholders. By codifying the recovery sequence, we remove the human element of hesitation during an emergency event, ensuring that the infrastructure behaves predictably when the environment is failing over. A recovery plan is fundamentally an ordered collection of steps that dictates how VMs are brought online at a secondary site. The most critical component here is the boot order, as many distributed applications require specific services to be available before dependent ones initiate. For instance, your database services must be fully operational before the application servers attempt to establish connections. Otherwise, those connection attempts will simply time out or fail. Within the Prism Central interface, you can categorize VMs into stages and set dependencies to control these timings precisely. This orchestration layer ensures that the startup sequence is enforced consistently every time, whether you are conducting a routine test or responding to a catastrophic loss of the production primary data center. Beyond simple boot order, the orchestration layer must address the inevitable reality of network addressing differences between disparate sites. When you move a virtual machine from one site to another, the underlying subnets often change, which traditionally requires manual intervention to update guest IP settings or DNS configurations. Nutanix Leap elegantly solves this by facilitating pre-configured network mapping, which automatically reassigns the virtual NIC to the appropriate destination network during the failover event. If you require a different IP address at the disaster recovery site, we apply IP mapping rules that orchestrate the guest OS changes, often leveraging Nutanix guest tools to finalize these settings. This capability allows the application to regain network connectivity almost immediately upon powering on, significantly reducing the downtime associated with manual reconfiguration steps. Complex recovery scenarios often require more than just powering on virtual machines and adjusting IP addresses to restore full functionality. Many legacy or highly customized environments require pre-boot or post-boot script execution to perform sanitization, update internal registry settings, or notify other parts of the infrastructure that a migration has occurred. Leap allows us to integrate these custom scripts directly into the recovery plan, creating a seamless workflow that executes automatically without operator intervention. These scripts can be triggered at different stages of the plan, providing the flexibility needed to handle bespoke application needs within a unified framework. Having these actions automated ensures that the environment is truly production-ready the moment the failover process completes. Effective disaster recovery is a hollow promise if it has not been validated through regular, non-disruptive testing. Prism Central allows us to create isolated networks specifically for testing purposes, which maps production VMs into a contained broadcast domain at the destination. By doing this, we can simulate a full failover, execute our boot sequences, and verify application health without creating duplicate IP conflicts or interfering with the live production traffic at the source site. These tests produce comprehensive reports detailing the time taken for each stage of the plan, providing evidence that our recovery time objectives are actually achievable. This testing capability is the cornerstone of business continuity as it transitions our recovery strategy from a theoretical design to a verified operational success. Finally, we must consider the nature of the failover and the subsequent return to production, which we call failback. Planned failover is a graceful transition where the source environment remains reachable, allowing for a synchronous final sync of data before the secondary site takes control. Conversely, an unplanned failover is a reactive measure taken during an actual site failure, where data loss might occur depending on the replication lag at the time the incident started. Once the primary site is restored, we execute a failback operation, which essentially reverses the replication flow and synchronizes any changes back to the original site. This orchestration ensures that the transition of services back to the primary location is handled with the same rigor and consistency as the initial recovery process. I look forward to our next discussion on how we implement these recovery mechanics. Welcome back to our exploration of the Nutanix ecosystem, where today we focus specifically on the practical mechanics of VM recovery and restoration. Understanding how to revert a virtual machine to a known good state is perhaps the most critical operational skill for any administrator, as it directly impacts your organization's resilience. When we approach the task of restoring a virtual machine, the first logical step involves interacting with the snapshots captured by your protection domains. If a virtual machine sustains data corruption or a catastrophic guest OS failure, you have the option to perform a full restore, which overwrites the current vDisks with the data from a chosen snapshot. This is a disruptive process because it effectively resets the identity and state of the VM back to the exact moment that the snapshot was created. Before initiating such a command within Prism, you must ensure that there are no active critical I/O operations that you cannot afford to lose, as the existing data will be permanently discarded during the restoration workflow. It is often safer to adopt a more conservative approach if the objective is simply to recover access to specific data files rather than the entire system image. A more surgical approach for handling data recovery involves the use of the clone from snapshot functionality, which is a powerful technique for creating a secondary, isolated instance of the virtual machine. By cloning from a previous point-in-time snapshot, Nutanix creates a new VM that exists independently of the original, allowing the administrator to inspect the state of the guest OS or retrieve particular records without modifying the production instance. This method serves as an excellent sandbox, providing a way to verify that a snapshot contains the required information before you commit to a full-scale restoration. Since the clone shares the initial data blocks via the metadata structure, the operation is virtually instantaneous, which is a significant advantage when you are under time pressure to mitigate an outage. Once you have successfully extracted the desired data from this cloned VM, you can decommission it, leaving your primary production environment completely undisturbed and operational. To minimize the administrative burden of file-level recovery, Nutanix provides a feature known as Self-Service Restore, or SSR, which distributes the responsibility of data recovery back to the users who own the virtual machines. When SSR is fully configured and integrated with Nutanix guest tools, it presents an automated interface within the guest operating system that allows file owners to browse available snapshots and restore individual files. From a technical perspective, this process automates the mounting of snapshot disks and the retrieval of file system-level objects without requiring the administrator to manually export vDisks or use secondary backup software. By empowering VM owners to perform these recoveries, you reduce the ticket volume for the infrastructure team while simultaneously slowing the clock on service restoration. This capability is deeply integrated into the AHV architecture, provided the required drivers are present in the guest operating system. In scenarios where human error leads to the deletion of a virtual machine, the Nutanix recycle bin serves as a fail-safe mechanism that prevents immediate, irreversible loss of data. When a VM is deleted, the administrator can navigate to the VM management dashboard to identify and recover entities that have been marked for deletion but not yet purged by the storage garbage collection process. This holding period provides a safety net that protects the metadata and virtual disk references, ensuring that you can restore these assets if the deletion was indeed accidental. It is important to emphasize that this feature requires no additional licensing or configuration, as it is a core component of the storage management design. Keeping track of the retention settings for this bin ensures that you have a verified window of opportunity to intervene before the blocks are eventually reclaimed for new writes by the cluster. When evaluating your recovery strategy, you should always favor non-destructive techniques like cloning or SSR over a full restore action whenever the situation permits. The restore action is a blunt instrument that should be reserved for scenarios where the virtual machine is fundamentally unreachable or compromised. By maintaining a clear distinction between the full recovery of an appliance and the surgical restoration of data, you maintain professional operational standards and minimize the risk of secondary data loss. These tools, when applied correctly, represent the difference between a minor incident and a significant architectural failure in your multi-cloud infrastructure. Mastering these techniques will undoubtedly simplify your daily operations and contribute significantly to your preparation for the exam. I will see you in the next session. Hello, everyone. And today we are focusing on the practical side of Nutanix guest tools and how they integrate into your infrastructure management. Nutanix guest tools, commonly referred to as NGT, represent a software bundle installed within a virtual machine to bridge the gap between the guest operating system and the Nutanix CVM, or controller VM. When you think about virtualization, you often encounter a disconnect where the hypervisor manages the container but remains somewhat blind to the granular activities occurring inside the guest OS. NGT resolves this by providing a unified communication channel that facilitates deeper integration and better orchestration. By deploying this bundle, you enable a suite of services that would otherwise be difficult to achieve through standard virtualization drivers alone. Think of it as providing your virtual machine with a native awareness of the Nutanix storage and management environment, which is fundamental for modern enterprise workloads. One of the most critical advantages of installing NGT is its support for application-consistent backups through VSS, or the Volume Shadow Copy service. In a typical backup scenario, taking a snapshot at the hypervisor level might lead to crash-consistent data, which is essentially the digital equivalent of pulling the power plug on a running server. While crash-consistent snapshots are often sufficient for simple workloads, databases, and transactional applications require a properly quiesced state to ensure data integrity. NGT communicates with the Windows VSS framework to flush buffers and complete pending write operations before the snapshot is taken, ensuring the backup is truly application consistent. This feature alone drastically reduces the risk of corruption when you need to restore your mission-critical applications to a previous point in time. Beyond backup consistency, NGT enables self-service restore, an essential feature for reducing the administrative burden on your IT team. SSR empowers end users or application owners to recover their own files and folders directly from within the guest OS, without needing to open a support ticket or wait for an administrator to mount a snapshot volume. When configured, an SSR agent retrieves metadata from the Nutanix cluster and presents the restore points as a local volume, making the process intuitive and transparent. This self-service model essentially shifts the responsibility of routine data retrieval away from the storage team, allowing them to focus on broader infrastructure health. It provides a layer of agility that is indispensable in fast-paced operational environments where data availability is a constant requirement. From a management perspective, NGT enhances the overall control you have over your virtual machines by providing advanced guest-level metadata. The CVM uses this connection to maintain a heartbeat, monitor uptime, and manage OS-specific information that would be otherwise inaccessible. Furthermore, NGT facilitates the automated updating of VirtIO drivers, which ensures that your virtual machines always run on a performant and secure stack. Without NGT, these updates would require manual intervention or secondary third-party tools, which complicates the lifecycle management of your guest operating systems. By centralizing these maintenance tasks, NGT helps keep the virtualized environment homogeneous and predictable, which is exactly what we want in a robust, hyper-converged infrastructure. Troubleshooting NGT often involves verifying the communication path between the guest OS and the internal Nutanix management network. NGT operates by utilizing a designated ISO that is mounted to the VM during installation, which contains the necessary binaries and configuration scripts. Once installed, the guest service establishes a secure connection to the CVM via a specific port, typically over the internal virtual switch. If you notice that an NGT-dependent feature like SSR is failing, the first point of check should always be the status indicator within the Prism interface. You should verify that the service is running inside the guest and that the CVM can reach the agent, as firewall settings or blocked ports can cause silent failures that hinder data protection capabilities. Always ensure that your guest environment meets the compatibility requirements for the specific AOS version you are running. If the versions between the NGT bundle and the AOS software drift too far apart, you may encounter issues with inconsistent reporting or failed snapshot attempts. It is good practice to include NGT verification as part of your standard pre-deployment checklist for new virtual machines. Monitoring these communication paths and keeping your guest tools updated will provide a consistent foundation for your data protection strategy. If everything is configured correctly, the integration remains invisible and reliable, providing the seamless experience that Nutanix is designed to deliver. I will see you in the next lecture. Hello, and welcome back. In this segment, we explore the integration of Nutanix Cloud Clusters, or NC2, with major public cloud providers. Nutanix Cloud Clusters extend the Nutanix software stack into AWS and Azure environments, effectively allowing you to run your hyper-converged infrastructure on bare metal instances provided by these hyperscalers. When you deploy NC2, you are not merely using a cloud-native service, but are extending the existing Prism management plane that you already use for your on-premises AOS clusters. This unification is significant because it removes the cognitive overhead of learning entirely new interfaces or operational models when moving workloads into the public cloud. From an architectural perspective, the Nutanix nodes in the cloud run the AHV Hypervisor and the Acropolis operating system just as they would in your local data center. This means that for your applications, the underlying hardware difference between physical servers and public cloud bare metal instances becomes largely transparent. By maintaining this consistent environment, You significantly simplify the underlying network configuration and storage management across these disparate locations. Essentially, you are treating the public cloud as just another extension of your existing data center footprint, which is the core promise of true hybrid cloud operations. One of the most compelling use cases for this architecture is extending your disaster recovery capabilities without requiring a secondary physical data center. Traditionally, maintaining a standby site involves substantial capital expenditure for hardware that remains largely idle until a failure occurs. With cloud-based clusters, you can maintain a scaled-down footprint in the cloud and only burst to full capacity when a recovery event is triggered by your orchestration tools. This capacity-on-demand approach also applies to scenarios where your on-premises environment faces unexpected spikes in demand. You can quickly add cloud-based nodes to your existing clusters to handle the overflow, essentially utilizing the cloud as an elastic backend for temporary resource requirements. Because the storage and networking abstractions are handled by the Nutanix software, you perform these migrations without refactoring your applications or modifying your image formats. This capability is vital for businesses that want to shift their infrastructure strategy toward agility while avoiding the technical debt often associated with cloud-native migration services that require substantial code changes. Managing cross-cloud networking involves establishing a robust connection between your on-premises environment and the virtual private cloud in the public provider's network. Nutanix handles the complexity of these connections by integrating with native cloud networking constructs while maintaining the logical overlay that your VMs expect. When you replicate data from an on-premises cluster to the cloud, you are utilizing your standard protection domains and replication policies, ensuring that the target cluster is always consistent with the source. The synchronization process leverages the same efficiency features you are accustomed to locally, such as deduplication and compression, before sending data over the dedicated connectivity link. This ensures that you are minimizing your egress costs while maintaining high performance for your critical workloads during the movement of data. By having a unified management view in Prism, you are able to monitor the health and throughput of these cross-cloud links just as easily as you would monitor a typical inter-switch link in your primary facility. See you in the next lecture. Welcome back to our journey through the Nutanix ecosystem. Today, we begin our focus on lifecycle management, a critical component for maintaining a healthy and secure cluster environment. In any distributed system, the complexity of managing software and firmware versions across multiple nodes and tiers is a significant operational burden. The Nutanix Lifecycle Management, or LCM framework, was designed specifically to eliminate the ambiguity and manual risk associated with these tasks. Rather than requiring administrators to track individual component compatibility matrices manually, LCM acts as an intelligent orchestration layer. It bridges the gap between the installed physical or virtual binaries and the desired state defined by Nutanix engineering. By automating discovery and dependency verification, this framework transforms what was once a dangerous maintenance window into a predictable and reliable procedure for the entire data center infrastructure. The architecture of LCM relies on two primary logical modules, which are the inventory module and the update module. The inventory module is responsible for the discovery process, where it scans every node in the cluster to identify currently running firmware, drivers, and software versions. It communicates with the Nutanix support portal to retrieve the latest metadata regarding component compatibility and available updates. Once this snapshot of the current state is reconciled against the metadata, the update module takes over, serving as the execution engine. This modular approach ensures that the system is always aware of the specific hardware configuration, including HBA controllers, NICs, and BMC versions, before attempting any modification. By decoupling the discovery process from the execution logic, the architecture maintains high availability even when connectivity to external repositories might be intermittent. One of the most profound benefits of this unified approach is that the process is inherently dependency-aware. In a traditional environment, updating a hypervisor or a firmware driver often requires a deep understanding of which components interact with one another. If you update the storage controller firmware without ensuring the driver version supports it, you inevitably face system instability. LCM eliminates this guesswork by validating the entire dependency tree before it executes even a single write operation. When you initiate an update, The cluster automatically verifies that all dependencies, such as the AOS version supporting the new firmware, are met and verified within the compatibility matrix. This holistic view ensures that the cluster remains in a stable, supported state throughout the entire lifecycle of the hardware. Navigating the lifecycle management dashboard within Prism is the first step toward effective cluster maintenance. When you open the dashboard, the initial view provides a comprehensive status of your infrastructure, highlighting any available updates or components that have fallen out of compliance. You trigger the inventory process manually or via a schedule to ensure the local metadata cache is synchronized with the latest Nutanix releases. Once the inventory completes, the interface presents a clear list of components that require attention, categorized by their potential impact, such as critical security patches or minor performance enhancements. This dashboard allows you to assess the current health of your entire fleet at a glance, providing the transparency required to plan your maintenance cycles with confidence and precision. See you in the next lecture. Welcome back, and let's examine the mechanics of maintaining a Nutanix cluster through the one-click upgrade orchestration. When we discuss the operational hygiene of a Nutanix multi-cloud environment, the ability to perform seamless, non-disruptive upgrades is perhaps the most significant feature in terms of reducing administrative burden. The one-click upgrade framework serves as the standard interface for updating AOS, the AHV Hypervisor, and Prism Central, abstracting the underlying complexity of patch management. Before initiating any upgrade, the system mandates a series of pre-upgrade health checks that verify the integrity of the cluster. These checks examine the controller virtual machine state, check for any ongoing metadata inconsistencies, and ensure that the storage pool has adequate space to handle potential temporary overhead. Data resiliency is the paramount concern here, so the system explicitly validates that your replication factor is satisfied and that no data blocks are in a degraded state. If the cluster detects an issue, such as a synchronization lag or a hardware fault that risks data loss, the upgrade process will be blocked until the problem is remediated. This safety-first approach prevents you from inadvertently escalating a minor hardware issue into a systemic outage. Treating the cluster as a living organism, we must respect these automated gatekeepers to ensure a stable, long-term deployment. Once the prerequisites are satisfied, the rolling upgrade process begins, which is an exercise in precise, automated orchestration across multiple nodes. The upgrade logic iterates through the cluster, updating one CVM or host at a time while leaving the rest of the cluster to handle the workload. If the target is an AHV upgrade, the system triggers a live migration of the virtual machines running on the host currently slated for maintenance. By utilizing live migration, the guest operating systems remain oblivious to the transition, maintaining their memory state and network connections throughout the reboot. This migration happens automatically provided that the VMs are configured with high availability and are not pinned to specific hosts in a way that violates migration policies. After the host is cleared of active VMs, it enters maintenance mode, performs the upgrade, reboots, and then rejoins the cluster to resume its duties. Throughout this sequence, the other nodes remain fully functional, continuously serving I/O requests and providing compute resources. The system manages this state machine carefully, only moving to the next node once the currently upgraded one has fully resumed normal operations and passed its post-upgrade validation tests. Monitoring the progression of these upgrades within Prism reveals how the system handles the inherent risks of distributed systems. The upgrade dashboard provides a real-time progress view, indicating which component is currently being targeted and whether the operation has successfully completed or encountered a stall. Behind the scenes, the cluster keeps track of the software versioning on every distinct node to prevent version skew that could jeopardize cluster stability. If an upgrade fails mid-process, the logic is usually designed to safely halt, leaving the remainder of the cluster either at the old version or in a consistent hybrid state, depending on the component in question. You have the ability to view detailed logs if an interruption occurs, which is essential for identifying whether the fault was a timeout caused by network congestion or a specific failure in service restart. Understanding this workflow is critical for the exam, as you are expected to know not just how to click the button, but how the cluster determines that it is safe to proceed. By isolating updates to individual nodes, Nutanix ensures that the aggregate service provided to the end users, the virtual machines, persists without interruption. Maintaining a consistent version across nodes is ultimately the final step, ensuring the cluster remains in a supported, high-performance configuration that follows best practices for cloud-scale infrastructure. I will see you in the next lecture. Welcome back. In this session, we will examine the mechanisms for keeping your Nutanix hardware components current and fully supported. Managing hardware, firmware, and drivers within a Nutanix environment is a task that requires both precision and a deep understanding of dependency chains. The Lifecycle Management, or LCM, framework acts as the centralized engine for these operations, abstracting the complexity of updating individual components like network interface cards, host bus adapters, solid-state drives, and the underlying BIOS or baseboard management controller. When you initiate an update through the Prism interface, LCM performs a series of validation checks to confirm that the proposed firmware version is compatible with your current AOS and hypervisor software versions. This reliance on the Nutanix compatibility matrix is not a mere suggestion. It is the fundamental constraint that prevents configuration drift and avoids the catastrophic failure states that occur when software layers become disconnected from their physical hardware expectations. By automating these updates, you minimize the human error factor inherent in manual flashing procedures, which often involve inconsistent execution across different nodes in a sprawling cluster. The orchestration of these updates occurs in a staged manner, ensuring that the cluster maintains high availability throughout the process. LCM assesses each node sequentially, verifying the health of the Nutanix CVM and the hypervisor before moving to the next physical host. If a driver or firmware update requires a node reboot, LCM integrates directly with the cluster's high availability features to move virtual machines to other healthy hosts in the cluster before taking the target node down for maintenance. This is the definition of a non-disruptive upgrade cycle. However, the stability of this process hinges on the accuracy of the inventory data collected by the LCM service. Before any update begins, the system scans the hardware to identify current versions and compares them against the repository metadata, effectively creating an audit trail of the hardware configuration state that is essential for both daily operations and long-term troubleshooting efforts. In many enterprise scenarios, particularly those involving financial or government sectors, the Nutanix cluster exists in an air-gapped environment with no direct connection to the public internet. This is where the concept of a dark site becomes vital for your operational success. A dark site configuration requires you to host the LCM repository metadata and software binaries on a local web server within your secure network. You must ensure that this local repository is kept in sync with the public Nutanix support portal, as the LCM service will point towards your internal URL instead of the default Nutanix backend. Setting this up correctly involves precise mapping of the repository files, as any mismatch in the directory structure can cause the local upgrade inventory to fail. It is an exercise in infrastructure discipline. You are essentially taking on the role of the update provider that Nutanix usually manages for internet-connected clusters. Coordinating your firmware strategy with your software lifecycle is an architectural decision that must be made well in advance of any maintenance window. I often see teams attempt to upgrade AOS while simultaneously patching firmware, but this approach introduces too many variables, making it difficult to isolate the cause if a component fails to initialize post-update. The more robust methodology is to maintain an update cadence that validates firmware compliance periodically, independent of major software feature upgrades. Always consult the Nutanix compatibility matrix before scheduling these tasks, as newer AOS releases may mandate specific minimum firmware versions for drivers to function correctly under load. Ignoring these dependencies often leads to intermittent performance degradation, which can be notoriously difficult to debug because the underlying hardware appears fine even when the driver software is suboptimal. Treating your firmware state as a first-class citizen alongside your VM configurations is the only way to ensure the long-term longevity of your hyper-converged architecture. See you in the next lecture. Welcome back to our exploration of system administration, where we will now shift our focus toward the critical domain of role-based access control within the Nutanix environment. Effective governance in a multi-cloud or virtualized infrastructure relies on the principle of least privilege, ensuring that users possess only the permissions necessary for their designated tasks. Within the Nutanix ecosystem, Prism Central acts as the primary control plane for defining these security boundaries, allowing administrators to move beyond basic local authentication. By leveraging robust identity and access management frameworks, An organization can mirror its internal hierarchy directly into the management fabric of the cluster. This process begins with the identification of user identities and the grouping of these individuals based on their operational functions. When we define these entities, we are essentially creating a mapping between organizational roles and the granular capabilities exposed by the Prism API and user interface. It is essential to treat these configurations not as static settings, but as dynamic components that evolve alongside your team structure. As we transition from local user management to centralized identity providers, we gain the ability to enforce consistent security policies across potentially sprawling environments. Proper implementation reduces the attack surface and minimizes the risk of accidental configuration drift caused by overprivileged administrative accounts. Integrating external identity providers such as Active Directory, LDAP, or SAML-based services represents a significant leap forward in standardizing infrastructure access. When you configure these providers in Prism Central, you are offloading the burden of credential lifecycle management to your existing enterprise security infrastructure. This architectural choice ensures that when an employee leaves the organization, their access to the Nutanix environment is revoked automatically upon the expiration of their directory account. During this integration process, it is standard practice to map these external groups to specific internal roles within Prism. For instance, an Active Directory group might be assigned a viewer role, providing read-only access to cluster health metrics, while a separate group might hold cluster administrator privileges. The flexibility of this mapping allows for nuanced control, ensuring that your security posture remains resilient even as the number of users grows. You must ensure that the communication between your host and the identity provider is appropriately secured to prevent interception or tampering. By centralizing authentication, you achieve a unified audit trail that simplifies compliance reporting and simplifies the overall management of user sessions. Beyond identity management, we must address the logical isolation of resources through categories and projects to achieve true multi-tenancy. Projects in Prism Central function as containers that logically group virtual machines, images, and networks, effectively creating a siloed environment for specific departments or internal customers. When you associate a role with a project, you are granting access strictly to the resources contained within that project, which is the cornerstone of department-level isolation. Categories further enhance this by providing a metadata-driven approach to grouping objects, which can then be used to automate the application of policies or security rules. Whether we are assigning a specific gold or silver service level to a virtual machine or isolating development environments from production, these mechanisms allow us to scale operations without sacrificing control. For a self-service end user, the existence of projects abstracts the complexity of the underlying infrastructure, allowing them to focus on deploying workloads within their resource quotas. Relying on these structures is particularly advantageous in hybrid or private cloud deployments where resource contention is a frequent concern. It requires careful planning to ensure that the project naming conventions and category hierarchies remain intuitive and manageable over the long term. Defining custom roles is the final piece of the puzzle, allowing you to tailor permissions with precision beyond the default system-defined roles. A custom role is essentially a collection of specific permissions, such as the ability to power on virtual machines, modify network configurations, or generate capacity reports. When creating these roles, you should perform a detailed analysis of what a specific user persona actually needs to accomplish their duties. For example, a developer might require permission to perform console access and clone virtual machines for testing purposes, but they rarely need the authority to modify storage fabric settings or update firmware. Creating roles based on these requirements prevents the common practice of granting broad administrative rights to users who only need scoped interactive session capabilities. Prism Central displays these permissions in a structured format, enabling you to toggle individual operations to build a custom security profile. Always favor creating roles that strictly adhere to the operational context of the user, as this simplifies the troubleshooting process when identifying denied operations. Periodic reviews of these custom roles are recommended to prune unnecessary permissions that may have been added during initial, less restrictive phases of deployment. See you in the next lecture. Welcome to this chapter, where we will examine the mechanisms Nutanix provides for maintaining a healthy environment and resolving operational issues through its support infrastructure. You will learn to navigate the support ecosystem, manage proactive telemetry, and leverage diagnostic tools to keep your clusters running optimally. Reliable operation of a complex distributed system like Nutanix AOS requires a shift from manual intervention toward integrated support channels. The Nutanix Support Portal serves as your primary interface for formal ticket management and accessing an extensive repository of knowledge base articles. When your internal monitoring indicates an anomaly, searching these articles is often the most efficient path to resolution, as they provide verified workarounds for common configuration errors or known software defects. Being comfortable with the portal's case management interface is vital for tracking communication history and ensuring that your organization effectively escalates critical issues to the site reliability engineering teams when pre-built solutions are insufficient. In modern infrastructure, waiting for a human to notice a fault is an anti-pattern, which is why Nutanix implements Pulse to handle proactive support. Pulse is an automated health monitoring service that collects system telemetry and sends it securely to Nutanix, allowing the vendor to identify potential issues before they cause service degradation. Beyond simple telemetry, the system can automatically generate support cases when specific alerts are triggered, effectively reducing your mean time to resolution by eliminating the lag between symptom detection and ticket creation. For this to function correctly, you must ensure that your cluster has appropriate outbound connectivity to the Nutanix support services, as a disconnected environment will inevitably lead to a lack of proactive oversight. While automated systems are powerful, there will always be situations requiring a manual deep dive into system health, which brings us to log bundle collection via Prism. When you open a high-priority support case, engineers will invariably request an NCC, Nutanix cluster check output, and a bundle of system logs to perform a root cause analysis. Prism provides a consolidated interface to trigger these log collections across the entire cluster, ensuring that the necessary debug information from every controller virtual machine is captured simultaneously. You should treat these bundles as the ground truth for state-based issues. They contain the serialized history of cluster operations, network latency snapshots, and service status that are necessary for identifying configuration drift or failed hardware components. The broader Nutanix community and the official documentation represent a decentralized extension of your troubleshooting toolkit that is often overlooked. Documentation is rarely just for installation. It constitutes the definitive specification of how features interact, which is critical when you are diagnosing unexpected behavior that might simply be a misunderstanding of how a specific policy is enforced. Engaging with the wider user community allows you to gain perspective on how others have navigated similar scale-out hurdles or complex integration challenges. By combining the structured knowledge provided by support engineers with the tactical experience of the user community, you build a resilient operational strategy that minimizes downtime and keeps your environment compliant with best practices. I look forward to discussing the next topic with you in our upcoming session. Welcome back to the course. Today, we will explore the essential mechanics of log collection and analysis within the Nutanix ecosystem. When we encounter anomalies in our infrastructure, the primary source of truth resides within the system, logs generated by the controller virtual machines and the AHV hypervisors. Navigating these logs effectively requires both an understanding of the available management interfaces and a proficiency with command line tools. Through the Prism Web Console, administrators can trigger log collection requests that encompass a broad range of cluster components, which is particularly useful for initial scoping when symptoms are vague. However, when we need to perform targeted troubleshooting, relying solely on the UI can sometimes obscure the granularity required to diagnose complex issues. This is where the log-by utility becomes indispensable, as it provides a structured and efficient method for gathering specific datasets across requested nodes. By employing log-by, you can generate a bundled diagnostic file that includes logs, core dumps, and system configuration snapshots, thereby minimizing the time spent manually traversing individual directories. To interact with log files directly on the controller virtual machine, one must possess a conceptual map of the directory structure, which is consistently organized under the home Nutanix data logs path. Within this structure, you will find logs separated by service names, such as Stargate, which handles I/O operations and storage latency, or Zeus, which manages the cluster configuration and state. When debugging storage latency, for instance, you should look for specific identifiers within the Stargate logs that indicate queue depths or abnormal request completion times. Network drops are similarly diagnosed by inspecting the logs associated with the open vSwitch or bridge configurations on the hypervisor host, often revealing packet loss or interface flapping events. Hypervisor errors frequently manifest in the libvirt or host logs, providing clear markers when a virtual machine fails to migrate or experiences a hard shutdown. Interpretation of these logs requires a methodical approach, ideally filtering entries by timestamps and specific error severity levels to isolate relevant events. Common log signatures are essentially patterns or repetitive strings that occur when a known error condition is triggered, such as a hardware timeout or a service heartbeat failure. By familiarizing yourself with these recurring signatures, you can expedite the resolution process significantly as you move away from passive reading towards active pattern matching. Always ensure that your clock synchronization across the cluster is accurate, as logs are timestamp-based records, and an offset between nodes can make correlating events across distributed services nearly impossible. While automated tools assist in collection, your ability to grep through text-based files and identify the causal sequence of events remains the core skill of a Nutanix administrator. When you are reviewing performance-related logs, pay close attention to the correlation between I/O patterns and the timing of latency spikes in the storage logs. If you notice a high concentration of errors during periods of heavy data replication or snapshot intervals, you might be looking at a resource contention issue rather than a failure of an underlying component. Advanced analysis involves stitching together these localized events to gain a holistic view of the cluster health, which enables informed decisions regarding hardware replacement or configuration refinements. Remember that logs are the primary diagnostic footprint left behind by the infrastructure software. Understanding how these records are synthesized is fundamental to maintaining a resilient multi-cloud environment. I will see you in the next lecture. Welcome back. In this session, we will examine the programmability of the Nutanix platform through its REST APIs and the orchestration capabilities provided by Calm. The Nutanix ecosystem exposes its functionality through two primary versions of the REST API, known as v2 and v3. While v2 is considered the legacy interface, it remains functional for several routine infrastructure tasks involving clusters and basic operations. The v3 API, however, adopts a more modern, entity-centric approach that utilizes a structured JSON schema to represent resources like VMs, images, and networks. Understanding the difference between these two is vital, because v3 provides the necessary granular control required for deep automation workflows in a multi-cloud environment. When you look at the Prism infrastructure, every action performed via the web interface is essentially a wrapper around a specific API call. By observing these interactions, you gain the ability to replicate those actions programmatically, effectively treating your infrastructure as code. This transition from manual interaction to scripted execution is the foundation upon which scalable automation is built. To begin working with these APIs, Prism provides a built-in tool called the API Explorer, which is an invaluable resource for developers and administrators. You can access this interface directly through the Prism Management Console, where it generates live documentation based on your specific cluster version. Before you ever write a line of script, use the Explorer to authenticate and perform test calls against your environment. This practice allows you to verify that your credentials work and that the payloads you intend to send are formatted correctly. You will notice that the Explorer provides sample request and response bodies in JSON format, which provides a clean template to copy into your automation scripts. By testing within this sandbox, you eliminate guesswork and ensure your integration projects start from a position of verified performance rather than trial and error. When it comes to the actual implementation of automation, Python and PowerShell remain the industry standards for interacting with the Nutanix REST interface. Using Python, you can utilize libraries such as request to handle HTTP methods like get, post, put, and delete with relative ease. For those embedded in a Microsoft ecosystem, the invoke REST method kmlet in PowerShell provides a seamless way to parse JSON responses into native objects. A common starting point for such scripts is automating VM provisioning, which involves defining a JSON payload that specifies CPU counts, memory allocation, virtual disks, and network interface configurations. Once your script constructs this payload, it submits the request to the Prism API endpoint, where the hypervisor handles the orchestration of the requested power on and resource reservation tasks. Robust scripts must handle authentication tokens efficiently, ensuring that you manage session timeouts and headers appropriately throughout the execution of your logic. Beyond simple scripting, Nutanix offers Calm as a dedicated solution for application orchestration and lifecycle management. While scripts are excellent for one-off tasks, Calm provides a declarative framework to manage the entire application stack, from the initial provisioning of infrastructure to the configuration of software within the virtual machines. It functions by using blueprints, which define the desired state of an application, including its networking, storage requirements, and sequence of deployment events. These blueprints are portable artifacts that allow you to deploy complex, multi-tier applications across different Nutanix environments or even across public cloud providers. By using predefined workflows, you reduce the risk of human error during the deployment process and ensure consistent configuration every time an application is launched. This level of automation elevates the role of the administrator from babysitting individual VMs to managing entire service catalogs that support organizational needs. The integration of API-driven automation and platform-level orchestration via Calm is what allows a modern data center to scale effectively. When you combine these tools, you move away from manual command line execution and into a strategy where infrastructure consistency is enforced by design. Status reporting is another significant advantage of this approach, as you can write automated jobs to query the API for resource health, disk latency, or cluster capacity metrics on a regular interval. Aggregating this data directly into your monitoring dashboards gives you a high-level overview of the ecosystem that would be difficult to maintain manually. Keep in mind that as you automate, you must also consider the security implications of your credentials and the necessary permissions that an API service account should hold. By keeping your automation modular and focused on specific tasks, you will find it easier to debug issues and maintain your workflows as the environment evolves. See you in the next lecture. Welcome to this chapter, where we will examine the principles and practical mechanics of Nutanix security hardening and continuous compliance. This segment is essential for any professional aiming to master the secure deployment, operation, and maintenance of a multi-cloud infrastructure environment. In this chapter, we explore how to translate high-level security mandates into concrete technical configurations within the Nutanix stack. Achieving a hardened state is not a checkbox exercise, but an architectural requirement that spans from the underlying hardware layer up to the management plane. We begin by looking at security technical implementation guides, commonly referred to as STIGs, which provide standardized hardening baselines. Nutanix simplifies this process by offering automated STIG compliance, which eliminates the manual, error-prone configuration of individual operating system parameters. When you enable STIG compliance, the system systematically applies hardened settings to the controller virtual machine and AHV host components. This ensures that your infrastructure adheres to strict security standards right out of the box, fulfilling the rigorous compliance needs of modern enterprise environments. Data integrity and privacy are further bolstered through data at rest encryption, or DARE, which is a fundamental component of a comprehensive security strategy. By encrypting the physical disks within the nodes, you render the data useless to unauthorized individuals who might physically access or steal the hardware. You must decide whether to use an internal key management service or an external one, depending on your organization's security policy and infrastructure maturity. Using an internal KMS is straightforward, as it is self-contained within the cluster, while an external KMS provides a more centralized control point consistent with enterprise-wide security governance. Once configured, DARE protects the data within your storage containers, ensuring that even if a drive is removed or replaced during a maintenance window, the sensitive information remains unreadable and secure. Maintaining a secured state over time requires more than just a one-time configuration, which is where Security Configuration Management Automation, or CMA, becomes vital. SCMA functions as an automated auditor that continuously monitors the configuration of your CVM and AHV host files against the applied STIG baselines. If a system configuration drifts from the hardened standard, perhaps due to an accidental manual change or an administrative mistake, SCMA automatically detects this deviation. It then takes immediate corrective action to revert the configuration back to the hardened state without requiring operator intervention. This closed-loop mechanism is the cornerstone of continuous compliance, as it effectively removes the human element from the equation of maintaining security posture in day-to-day operations. Securing the management network and the surrounding infrastructure components against unauthorized access forms the final pillar of our discussion. It is a best practice to isolate the management traffic of the controller virtual machines and AHV hosts onto a dedicated management network, separate from production VM traffic. This isolation reduces the attack surface by ensuring that management interfaces are not routable from general-purpose or user-facing networks. Access to these management interfaces should be restricted through rigorous implementation of the principle of least privilege, ensuring that only necessary administrative accounts have entry. Furthermore, regularly patching your systems and auditing service access points prevents attackers from exploiting known vulnerabilities or misconfigured management services in your software-defined data center. See you in the next lecture. Welcome back. As we reach the final stage of our preparation journey, we will consolidate our understanding of the Nutanix ecosystem to ensure you are ready for the professional certification exam. In this concluding session, we will synthesize the architecture, storage, networking, data protection, and lifecycle management domains that constitute the core of the NCP-MCI version 6.5 curriculum. Efficiency in the exam environment often hinges on your ability to synthesize disparate pieces of information, such as how storage containers interact with data reduction settings or how network security policies define microsegmentation scopes. Throughout this course, we have walked through the technical intricacies of AOS and AHV, but it is the cohesive view of the cluster that matters most when you are faced with architectural design questions. If you find yourself struggling with a specific concept during the exam, recall the fundamental relationship between the controller VM and the distributed storage fabric. Many of the questions you will encounter are designed to test your diagnostic intuition rather than your ability to memorize static tables. Think of your knowledge as a set of building blocks where the command line interfaces like NCLI and ACLI serve as the essential tools to manipulate the underlying infrastructure. Revisit the logic applied to virtual machine management, specifically focusing on how high availability events interact with snapshots and protection domains. A successful candidate understands that the Nutanix environment is inherently modular, so keeping the interaction between these layers front and center will significantly improve your accuracy. When approaching the exam, time management is just as critical as your grasp of the material itself. You may notice that certain questions require you to analyze a scenario and identify the most appropriate administrative action, which implies that you need to be familiar with the Prism interface and the specific paths to configuration menus. Do not spend excessive time on questions where the answer is not immediately apparent. Mark them, proceed through the exam, and return to them with a fresh perspective. The exam often presents complex multi-part questions, and it is helpful to look for keywords that define the scope of the problem. For instance, if a question mentions data reduction, consider whether the trade-offs in performance or storage capacity are explicitly being tested. Utilize the process of elimination by identifying the provided distractors that clearly violate the design constraints of a Nutanix cluster. Even when you are confident, take a second to verify that you have understood the entire context of the problem, as small details regarding hypervisor support or hardware compatibility can change the correct path. Maintenance and lifecycle operations are frequent topics that test your operational rigor and understanding of institutional reliability. Remember that LCM is not merely about clicking a button, but about orchestrating the update process safely across a distributed environment while respecting the availability requirements of your workloads. When dealing with firmware or driver updates, focus on the dependencies that these tasks might introduce to the storage fabric. Reviewing your understanding of role-based access control and security hardening is also essential, as the exam frequently tests whether an administrator understands the principle of least privilege. Data protection scenarios often involve snapshots, replication schedules, and recovery points, so keep the distinction between synchronous and asynchronous operations clear in your mind. If a specific recovery scenario is presented, evaluate the replication lag and RPO requirements before selecting a solution. These concepts rely on the underlying architecture, so if you're unsure, mapping the data path from the VM to the storage container is usually a reliable way to ground your answer. As you prepare for the final evaluation, treat your practical experience as the primary source of truth. The exam is structured to reward those who understand why a particular feature is used rather than just knowing how to toggle a switch. If you have any remaining gaps in your knowledge, direct your focus toward the official Nutanix documentation, specifically the sections covering cluster health monitoring and performance reporting. Understanding how logs are collected and where to find them can be the difference between a correct and incorrect answer in troubleshooting scenarios. Maintaining your professional certification status is a commitment to keeping pace with these changes. So continue to monitor the release notes and technical articles provided by the community. Stay disciplined in your review and ensure that you are comfortable operating within the CLI for those edge cases where the graphical interface might not provide the full picture. Success is a product of consistent effort and a clear understanding of the architectural philosophy that Nutanix employs. Good luck with your final review and your upcoming examination.